All right, all right. Hello, everybody. Welcome to the stream. We got some music today. Welcome. Little music to introduce. Welcome once again. Another meeting. Here we meet again. Almost as if this was a company. And yay! Welcome now. How is everyone doing today? I see you, Penguin Operator. I'm so sorry. I finished the stream. I clicked the stop streaming button accidentally, and yeah, it was unfortunate. But now we're back. We're so back. We're so back. Yeah, everyone is doing well and fine. And yay! Today is the weekend. It's the weekend, which means we're able to get a lot of work done. So let's go. Yay. Wait, I think the scenes are working. Yes. Yo, hello. I see. Why is this thing offset? It should not be like that. Let me move it. So, you see how the chat is positioned too much to the right? There you go. Something like that is better. Well, a little in the middle. There you go. Okay. That's perfect. And then, in the coding scene, here. There you go. Perfect. Yo. All right. All right. Let's go. Okay. So welcome everyone back today. Today we're going to make the biggest stretch we've done for the memory allocator, hopefully. I want to finish the memory allocator because we've spent already many streams and we're nearing the end since we wrote malloc already and kind of tested it. We wrote free already and kind of tested it. And we're writing Realloc. We already wrote Realloc, and now we are kind of testing it. Then after that, we just need to create automatic tests for all of them. And once that's done, we will be able to consider ourselves free. So, yeah, I don't know. This is perfect. All right. Let's begin then. Let's begin. So. Here we were yesterday. We were fixing an assert problem that fortunately we had that assert because, it was a little bit of a difficult to catch problem. There was a weird thing going on with how we calculated whether or not the current block was free. And now we transition to try and test Realloc, right? So we have this little toy example where we're going to have 3 blocks right next to each other of the same size. We're going to write stuff into them so that we can identify them. And then we're going to free the one on the left, free the one on the right, and see what happens when we realloc the middle one. Okay? So we haven't even run this because yesterday I really had to go and yeah, we had been a little bit rushed. But now I think we're able to see what this test is going to do. So we're going to introduce a breakpoint here. And we're going to try and see what happens. So I think if I just delete all breakpoints and only break here, we're going to be able to observe the behavior. So no, I have to give my password. 1, 2, 3, 4. Yeah. All right. So first thing we do is we create some sort of fictional heap with malloc, because this is just for the sake of testing. And then we perform all of these until we get to the breakpoint. So now, ideally, we want to enter the memory inspector and take a look at the memory that we currently have. That it's like our heap, right? So 0x 1 2 3 4 6 1 9 1 2 3 456 A80. Perfect. Okay. So here we initialize our memory, right? Then over here, so notice that all of this data is from like the previous tests. But over here we allocate 40 bytes. So we should see the 7D turn into the actual thing it should be, which is, 40 bytes. Perfect. So 2D, 2C. Awesome. Now, is 2D 40? So 2 times 16, yeah, 32. And then that plus it's not 40. It seems to be more like 44, which is exactly what it should be because plus the 4 bytes of the header, that gives you 48, which is 8 byte aligned. Great. Now we allocate 40 more bytes. So again, 2D and then 2C. And then P3, which should be again 2D and then 2C. Why are they different? Oh, because the header has the 3-bit set to true. So it's pretty important. Yeah, I think so. So hello again, Fanbjerg. Welcome to the stream, and welcome everyone that's joining. So today we are doing, we're living a little bit the simple life. We are. It's a little bit relaxed since it's the weekend, and we don't really have to worry about much. At least not on my side. So I think this is going to be a pretty long stream because hopefully we'll be able to finish the memory allocator between today and tomorrow. I'm going to aim for today, but as always, like whenever a programmer tells you, "Oh yeah, this is gonna be done really soon," do not believe them. So similar. I mean, I'm gonna aim to finish this today, but I'm pretty sure we're going to have to extend it until tomorrow. I successfully bytecoded the demo of my Vulkan implementation yesterday in Opus 4.8. It's a bit unstable, a bit laggy, but something pops up on the screen. Oh, congratulations! You've been updating us on your progress on it, and I'm glad to know it's a little bit more, taking shape. So I wrote around 200 lines of code, didn't see my triangle, get impatient, told AI to just copy the tutorial for me. Right, funny. Let's see. Try and. Yep. Okay. All right. All right. Wait. Oh, yeah. Okay. Sorry. So over here, what we're doing is we're writing, all of the information we need to the memory box. So here we write the second one, and then we write the third one. So remember, AA, and I feel like you can take a look at it if I move the camera. Oh, if I move the camera over here, you can take a look at what we can see, which is the actual ASCII representation of what's being stored. So remember, this is a 40 byte long message, AA. So if it finishes in AA, it was originally in P1. If it finishes in BB, it was originally in P2. And if it finishes in CC, it was originally in P3, right? So given that, just remember where the messages should be because we're going to realloc stuff. So it's going to be moved around. Here we're going to free P1. So P1 is now free. Then we go to free P3. And so we should see P3 being free, which is indeed true. You can see it illuminates on the places that have changed in memory. And now we're going to try and realloc P2. And for this, we want to enter the function to evaluate every single line's behavior. And it seems like either this is really slow or we had a problem here. It says error, apply non-zero offset 24 to a null pointer. That may have just been the watch variable since I had break free and then equals true. So I think we're fine. Luckily, since I copied from the tutorial directly, it is still maintainable for me. More of the time I understand it. Pretty good. Yeah, that is an ideal situation. Um, Here when we're looking at Realloc, we want to reallocate this block P2 to be 65 bytes. So of course that's going to change since we need to align it. And the size that ends up being determined is 68, because 68 plus 4 is going to be 72, which is 8-byte alignment. Yeah, 63, yeah, 9 times 8. Yeah. Now we're going to obtain the previous block to P2. So remember that P2 starts, let's see, where does it start? So it's a byte long message AA. This, okay, so P2 starts here. Should be this guy. So P2 starts here, right? Right here, on where the 2F is written. So when we look at the previous block, we want to see this, block number 1, which starts at address 24. So P block should be 24, perfect. And then P3 should be over here, this 2C. Hi, Nicholas, welcome to the stream. I'm glad you're joining. Currently, we are testing Realloc. We have like a little toy example because yesterday we were not able to run it. And so today we're taking a look at that example. Everything seems to be working for now, but we just started, which means that, of course, we're going to discover some stuff. So here we have the next block. So the next block should be block number, let's see, block number 24. 24 plus 16, 30, 46, and then 62, I think. And then 62 plus that would be 78, 90, and then it should be 102. So either 102, 103, 104, the one off by one I may be, but it should be something like that. 120. Ooh. That does not look too good. Actually, maybe it does. Let's see. 16, 32, 60, 48, 64, 64, then we have 80, right, and then 96. Oh, actually, no, it adds up. Yeah, 96, 112, and then 13, 14, 15, 16, 17, 18, 19, 20. Yeah, it's correct. So we grab indeed the correct blocks. And now what we do is we say, well, the size of my current block is, in fact, I think we can just, the current block is 72. So if we do like BK size of our block, you notice that it's 44, which is not enough to accommodate for the size that the user is asking to reallocate, which is originally 65, but to a by line 68. Gorgeous self-interest, gal. AI views and streamed on. Okay, buddy. You're getting banned. Bam. All right, bye-bye. Yeah. Anyways. As we were saying, so we're going to do, the size of the block, but we see that this is not true, right? Our block is not able to accommodate for it. So we skip it, yes. Now we see if merging with the right block is enough. In this case, it is, because each block is 44 long. We try to accommodate for 68. So we're going to have more than enough space. So hopefully we're able to enter this if. Perfect. Now we remove from it the next block, which indeed happens, and then we coalesce them. So this 2F should change to almost double. Yeah, okay, 5F. Just seems reasonable because you have to also account for the fact that the header of the next block also gets added to the size. So now the size is even bigger. So it's 44 plus 44 of the other block plus whatever the header was. So it's 88 plus the 4 bytes of the header, and that's 92. So indeed, we have the correct thing. Now, It's a 92 by block, but then I want to accommodate only 68, right? And so we determine whether or not we want to partition by calling partition of worth it. And we see that, yes, indeed, we do want to partition. It is, a pretty big block compared to what you actually need. And thus, we're going to grab that block. We set it to be free, right? Oh, which is interesting. It partitioned it to fit exactly what the request was. The block is set to be free. And then we insert into the red black tree this right block. Perfect. And so out of all blocks, yeah, number 1 should be the root, and then this guy should be after. Perfect. And now we return that pointer, which should be the exact same pointer. So char p2 underscore should be the exact same, and that's why we have this assert. Yes, perfect. And so now in this block, which is block 47, like this guy that has a 47, we're going to write down all of this string just to identify it as sort of the new guy. And yes, all of that information is now written there. And unfortunately, because this is where the new block starts, if I remember correctly. 14. So, yeah. Now, we're going to try and reallocate P2 to have 84 bytes. The only block that's free is the first block. And so it's going to try and merge with that first block, and we have to see that it takes the right path. So the size we're asking for is 84. We need to align this, and it remains 84 after alignment. So we grab the block that we're looking at, which is still block 72, because it hasn't changed. And the previous block should be block 24. The next block should be null. Ooh. Oh, never mind. We did partition the block in order to get this. Is P3 invalid after P2 realloc? Yes. So after the realloc has happened, yes, because we freed P3. So it's fair game for, it's fair game after this point. Yeah, and welcome, Vicente de Alencar. I remember seeing you in a previous stream, so welcome back. And over here, where what we're going to do is, we're going to calculate how much space do we actually need. Right? The amount of space needed is 84, which is the size that we need, plus the 4 bytes at the header. So that's going to be 88 in total. Now, if the block size, if a block is already able to accommodate for that size, then, we can just shrink it. But that's really not the case, right? A block is size 68 and we need 88. So no. Now, if we expand to the right, would we be able to accommodate for this? It is a great question because we partitioned the block before and the block to our right has, I think, 20, right? It has a size of 20. So I think this is another case where it is indeed possible to accommodate the block by just merging with the right. Yeah. So we remove it from the red black tree, we coalesce the blocks together, we merge them together now, and then we try to partition of worth it. The answer should be no. Thus, right block should be a null heap pointer. Yes, perfect. And then we simply return what we have. And that's it. Okay, so it's able to realloc and to do all of this stuff, even when it, previously partitioned the block and all of that happened. So I feel this is solid. Let's call this test realloc 1. And then let's create another one called test realloc 2. And so what we're going to do is we can definitely copy sort of the setup, right? The exact same setup. But now we want to exercise the left, right? So we want to see what happens when you need to merge with the left. So over here, what happens if instead of freeing P3, we just don't free P3, and then trigger a reallocation of P2. So then P2, the only block that's free is the one to its left. So then it would have to copy all the information over to P1. Yeah, so let's do that. And then we need to assert sort of that the new pointer that you give me is exactly the same as P1, right? P1 is invalidated, but we're not going to dereference it or anything. We just want the value of the pointer to be the exact same. Not only that, but we also want to test what happens if after this we free P3, right? And then try to expand P2 again. Realloc. Then I want to reallocate P2 underscore to something that is, I don't know, 110 bytes long, right? So it is going to need to merge with that guy, right? And so after that happens, I think we should be able to write a message that's rather long, and the memory sanitizer should not complain. So let's just do something like a message. Never mind. It's actually 110, or at least I think. And then we're gonna put a happy face, and then an exclamation mark. Perfect. Or I think there you go. Okay, I think this is a 19 character message. 109. No, it's 82. Okay, it doesn't matter. As long as we gonna just write random stuff to complete 109 so that we can see it. So 102, 3, 4, 5, 6, 7, 8, 9. Perfect. And so now what we're going to do is we see that everything is copied there, and in fact, this is not P3. This is supposed to be this. Great. Okay, I think this would be another decent test. So, oh my god, 20 years. Hello, everyone. Welcome. The weekend is here. And today we're going to have a very, very helpful debugging session. We're simply going to test our Realloc since yesterday I had to rush out. But yeah. And so this test over here, what we're going to do is we're going to free the left, see if we actually merge with the left, see that the block becomes really big. So then we partition that block and there's going to be a one mini guy left, and then verify that that mini guy gets merged with the guy on the right to create a bigger free block. Once that's happened, we're going to, this huge block we reallocated already, we're going to free P3, which is the only free block left, and then reallocate that guy, right, to, P2. And so we should see the two merging. So the huge block merging with the only remaining free block, and then we should be able to set the information there. So now what we can do is we can return true if all of this happens and is approved. All right. So something I do want to assert is that this doesn't really move, right? The pointer is exactly the same. Given that, let's go to the terminal and let's execute it. No, let's compile it. There you go. Test Realloc 2. Perfect. Now we run this. Let's reset. So we eliminate all the watch variables because then the sanitizer is going to complain. And let's run it. So here we want to stop at not test Realloc 1, because that one we've already seen, but test Realloc 2. Right here. Perfect. So let's wait. Awesome. Okay, so now we have the heap, right? Now that we know the heap, let's go to a memory inspector and try and create a view for that, part of memory. Let me add it, and it should be 0x1234 619 1234 1234 56880. There should be a lot of information that just comes from. Oh yeah, there's no information. Never mind. So we run test 3, and after the 3 test runs, our memory is gonna look like this. The same thing happens here. We test Realloc 1, right? And now we test Realloc 2, and this is what we're interested in. So we're going to initialize memory. Then we're going to allocate P1, which should make this, a 2D, but it's already there, so it shouldn't change anything, except for, the fact that there's no root. Then we allocate P2, which should change this, I think it's this 5F or the 67 that it should change to 2D. Yeah, 5F to 2D. And then P3 should change this 74 to a 2D. Ooh, a 2C. Why? Let me think. Oh, I think it's fine. I think it's because of the previous 3. I think, although I'm not quite sure why it's 2C instead of 2D. Because a struct has the size, the previous 3, and then the color. And they differ by 1. Oh yeah, so the color doesn't really matter. Okay. Perfect. So now what we're going to do is we're going to say, well, we write the information into each of them. So you can see over here, this is a 40 by log message AA. Then we write the same for BB. Then we write the same for CC, right? So remember, AA belongs to P1, BB belongs to P2, and CC belongs to P3. Now we're going to free P1, which means that we should see a change in the member variables of this to all becoming FF. Yes, perfect. Then we're going to reallocate P2. So what is it that we should see? Well, we should see, first of all, this thing become an FFs because the root, it's like, it gets nullified. It says, oh, there's no longer a root since the only block that I had freed is no longer free. So the red black tree for free blocks is empty. And we should also see the size of 2D become something like 5D, something around the ballpark of double the value, plus 4 more bytes. So let's reallocate, right? Let's enter this function and see that it does the thing and it should. So the size that we're asking for is 65, but we need to 8-byte align this. So that should be 68. And 68 plus 4 gives you 72, which is 8-byte aligned. And now we're going to calculate which block we're talking about. So we're talking about block, if I remember correctly, block 72, something like that. Yeah, block 72. Our previous block should be block 24. And the next block should be something like 90 something. Yeah, 120. Okay. Now we calculate the space needed, which is going to be 72, right? Because that's, the 68 we're asking for plus the 4 bytes of the header. So that's 72. And then we're going to say, well, if our current block is already able to accommodate for this, then no need to reallocate anything. But the current size of a block is 44. So definitely not. We skip this. We take a look at our right and we say, okay, if we're able to, when merging with the right block, accommodate for this request, then do it. But in this case, our right block, which is P3, is not free. So we should be able to skip this. Perfect. And now we say, well, is our left block available? If so, then let's merge with it and then, proceed. In this case, yes, our left block is P1, so we should be able to see that it's free and that if we merge with it, we're able to accommodate for the size that's needed. And thus we get, we enter this if. So we first get the previous size of the block, which should be 44. Yes. Then we remove our previous block, which is P1 from the red black tree, because we're going to say this guy is no longer free. Then we're going to copy the info that's in the footer to this variable because it's possible that it gets overridden. Then we try to coalesce the blocks, right? So we merge them together, which changes this 2D to be something around double. Ooh. Ooh. Okay. Okay. We have a problem. So in coalesce blocks, we created this assert that was something like you're only able to merge blocks if the leftmost one is free and the rightmost is free, or if the leftmost one is occupied and the rightmost is free. So I think we did this just to make sure that when we created Realloc, we knew what we were doing. This assertion is no longer needed. And the reason for that is that we can coalesce any type of blocks. Right? We can coalesce two blocks that are occupied. We can coalesce a block that's free and so on. Sorry. We can coalesce a block that's free and a block that's not free and so on. But ideally, in a mental model, we want to make sure that we don't override user information by doing this. So that's what the assert was sort of making sure that, we don't do crazy stuff. Nonetheless, we see that Realloc introduces a different situation where this could be completely valid. I think that rather than this condition, that checking that the second block is always free, is more like one of your blocks has to be free. Right? Because if you're trying to merge two blocks that are allocated, then we're in trouble, right? Because you're definitely overriding user information in some sort of sense. So you're only allowed to coalesce blocks if that means you're expanding a block in some sort of way. And expansion requires one of the two blocks to be free, right? So that you don't override any sort of information. So I think that's reasonable to assume. And thus we can run this again. I think I'm just gonna skip to the part where we were, because everything was going well up until that point. So yeah, here on the expansion, I think it was, yeah. Okay, so let's run main, and let's go here. Then we do all of this. And yes, I know, memory inspector. So we free this guy, then we continue, then we realloc here, and this is the one that we're looking at. Perfect. Now let's take a look at the memory inspector in the new memory view, because it's different. So it's 0x 1234 619 1234 56880. Perfect. So now size is exactly the same. Block 72, P block is 24, and next block is going to be 120. Yeah, the space needed is 72. We skip this because we don't shrink. We skip this because the right is occupied, and we enter this because we know that the left works. Now we grab the previous size, we remove it. We saw this already. Now we copy the user's info that they have stored in the footer. So inside this 2F guy, I don't think we have any information that's, going over the footer. So copying this wouldn't be that useful. And then we coalesce the blocks. So when we coalesce the blocks, we should see this 2D change to something like, 2C plus 2C or something like that. Yeah, 5D. Okay, so because plus the 4 bytes of the header. Then we're going to say, well, is this too big of a block for the actual request? So the space that you need is 72, and the size that you're asking for is 68. And this is going to be like a 92 sized block, right? So if we try to do BK size with the block that's in pointer 24, it's 92. So definitely, it is kind of worth it to partition. Because if we partition, then we're going to have another block. Because, we cannot just give one huge block to the user. We need to say, okay, right, is this block too big for the user's request? If so, then partition that block and then leave the remaining as a free block. So that's what we're going to do here. And in this case, it should identify that this is too big of a block partition it and then provide to the user the part that is better for them. And we see a problem. So when we partition the block, we're asserting that the block that we try to partition is not free. Um, Okay, so the reason why we were doing this is because we want to make sure that whatever happens when it comes to partitioning the block needs to happen for a block that is not in the red black tree. CTFERZ or CTFERZ. Hello, welcome to the chat. As this is your first time, I'm gonna watch your YouTube videos. Hopefully, I can catch up and grasp my head around it. Yo, perfect! You discovered the YouTube channel. That's great. So we have a YouTube channel where I just upload all of the VODs, so that you can take a look at it if you want at some point in time. But yeah, wait, I'm glad you come from the YouTube, and thank you very much for following. So yeah, currently we're taking a look at the tests of our realloc function. So trying to reallocate stuff in memory. And we're currently taking a look at, debugging everything as seen. So this function partition block, right? We want to partition a block that is not in the red black tree. If that block is in the red black tree, then we're in trouble and in big trouble. The reason is partition block does not concern itself with the red black tree, which means that the partition is not guaranteed to keep alive the metadata that refers to it. So once we partition the block, that metadata of the left, right, and parent nodes is potentially corrupted. So we perform this assert to say, make sure that you do this with a block that's not in the red black tree. Now, previously, our notion was something is free if and only if it is in the red black tree. Now it has changed. If it is in the red, like something is in the red black tree, then it is free. The converse doesn't hold, right? Because we could have a block that is free, like in a case, right, where we're trying to expand it, but that is currently not in the red black tree. And what I mean by that is, notice that when we want to expand the block, we grab the block that's free to which we want to expand to. We remove it from the red black tree because we know that its metadata is going to get corrupted. But that block is still free, despite not being in the red black tree. Then we perform the expansion, and then we reinsert in the red black tree. So this assertion is assuming that you're free if and only if you are in the red black tree. That is not the case. Like at least no, not anymore. Emmanuel Pinen, hello, welcome to the stream, and thank you for following. Yo. But yeah, so that is why that assertion is living there. And I think we should be fine with removing it. We just have to make sure that the metadata related to the red black tree is no longer, is no longer. And in fact, that's what the remark in the oxygen says. Now, this function corrupts the red black tree metadata as well as curve 3. Right? Like, be careful. Curve 3 doesn't exist anymore. So then we simply say, the function corrupts the red black tree metadata. You're welcome from West Africa. Whoa, yo, we're going international, guys. Yo, let's go. Perfect. What time is it there? It's like around, I think you guys maybe 7 or 8 hours into the future. So probably something like 2 p.m. or 3 p.m. I'm not sure. Or more like 5. But yeah. Yo, I'm glad you're joining the stream. So let's go. Yeah, 2 p.m. Oh yeah. Around that time. Perfect. Well, about to be 3. Yeah. So awesome. All right. I think if we get rid of that assert, we make life not only simpler but correct. Like in the sense that the assert is no longer valid, but it's good that it was there, so we could check our assumptions. Yeah, because there's nothing else in this function that relies on it. So we run the heap, all of this we already know. I'm just going to allocate all of that, and then we're going to run to the realloc part. We're going to enter it. Now I want to go to the memory inspector. Oh, sorry. Let's go now to the memory inspector and create a new view for the actual memory we have, which is 0x. Oh, it's the same. Oh, I shouldn't have done that. 619, 1, 2, 3, 4, 5, 6, and then A80. Perfect. Great. And so now what we're going to do is we're going to reallocate, right? We perform the size calculation. So all of this, we already know what the values are. This is going to be 120. Space needed 72. We skip this, we enter here. There you go, the previous size. We remove it from the red black tree. We set this to, we copy the information to a variable, then we coalesce the blocks together. And then once we coalesce them, yes, we see 5D, which means it was expanded. We should be able to see that the allocator deems it worthy of partitioning this block. So right block should be the pointer to whatever the new free block is that remains after the partition. That's 96, yeah, which is correct. It's the perfect. And so now we say, well, yes, this is a free block. P3 is no longer free. Sorry, yeah, P3 is not free yet. So this guy should not merge with P3 yet. Right, perfect. Then we set it to be free, and then we reinsert it into the red black tree to indicate that it's a free block. So awesome. And now what we need to do is we need to copy the data. So remember that P1 contains the string, this is a 40 byte long message, AA. P2 contains this one, but ends in BB. So we should be able to see how this information that I'm pointing at with my mouse, right, that this AA changes to BB once we're done. So we continue, right? We grab the pointer to the user section of where the user has its data and in the current block. And then we grab the pointer to the user section of our previous block. And so let's take a look and see if those pointers are correct. So 61900 ACC. ACC. And in fact, notice that it points exactly to the beginning of some user section. This is a 40 byte, right? So let's continue and see what happens. So we move the information from, well, to the previous block. I think that's the syntax, right? Destination, source, and then the size. So we're gonna move it to the previous block. It's gonna come from the current block, and it's gonna be however long that block was. Then we do that. And what we see is this is a 40-bit D. No. So it seems like it's totally incorrect. Well, so it seems like we corrupted the user data that was in the middle block. At what point in time did that happen? And why was it in the coalescing? I'm pretty sure it was the coalescing that messed up everything. I think, where did it happen? Ooh, it may have happened in the partition, was it? Okay, I'm not sure. Let's run it again. Let's run it again and see. So pay attention to the memory values here on the right. I think these guys. Because let's see. If we run, right, we skip this part. And then we try to get to the realloc. So we allocate the blocks, etc. Then we write the messages. So there goes this is a 40 byte long message AA. So this one's correct. Then the next one is P2, which writes, this is a 40 byte long message BB, right? So P2 has that information, and then the same for P3, just with CC. P1 gets freed, so if that information is corrupted, we don't really care. And now we need to make sure that BB doesn't sort of get corrupted, right? So this BB should remain. let's enter Realloc and let's see where does it change and where does it get corrupted. So we grab the blocks we need. These are non-modifying things. We don't shrink, so we skip this. We don't expand to the right. We actually need to expand to the left. So we enter here. And then we enter this if, yes. Calculate the previous size. Removing the previous block from the red-black tree should be completely fine. We copy whatever information's in the footer, which is fine too. And then we coalesce the blocks. And this should not change information except for maybe the footer, which would be this BB and then this exclamation marks and etc. But this is a 40 byte long message, should not change. Okay, fine, it's still there. And then when we partition, which is orientation, that's where it happens, that's where we introduce the problem, right? Because if we partition, I think that we partition before we copy the data. And so, but that should still be fine, right? Because partitioning, actually, no, that is the problem. That is the problem. We need to copy the data over before we partition. Because when we partition, we're going to free the sort of the last bytes of the block that are extra. But currently, our information is living in those extra bytes. So when we partition and then we make that free, we corrupt all of that, the user memory because we partition before even copying the data. So before that happens, we need to have this section be there, right? So then before partitioning, merge the two together, copy the user's info into the actual new block. Perfect. And now we partition if it's necessary, and then we return. And what we return would have to be, I guess, I'm just gonna do, we already have the block uPointer variable, so I think I can just return that. Perfect, perfect. So now it should work, guys. I promise. I promise it will work. Okay, no, I don't promise anything because we don't know. But yeah, let's run it again and see what happens. Now, I think we can skip most of it. So let's go here, then we go M a minute. We now look, we write the message to memory. So I think it's so good that the heap is the exact same value, so we don't have to refresh the memory inspector. Okay, so we continue. And then we free P1, and then we realloc P2. So let's enter that. This, daily life, we already know about it. We know that we don't need to shrink, so we don't shrink. Then we know we don't need to expand, so we don't expand. And I think camera's getting a little in the way. I think I'm gonna put the camera over here. Yay, I feel that's perfect. Okay, there you guys can see the code. Sorry about that. So now, what we're going to do is we're going to enter this if, because we do need to merge with the left, or with the previous block. Calculate the size, remove from the tree, right? Coalesce the blocks. We should see a 5D somewhere. Yeah, here, 5D. And then after that, we calculate their user sections, and then we try and copy the data. So that's going to be this mem move. Notice that this BB should now be living where this AA is, and the entire message should make sense. So let's run it. Perfect. This is a 40 byte long message, and then BB, and then the 3 exclamation marks. Perfect. And now we copy the footer too. But that's not going to be that necessary because, nothing changed in the footer. Like, at least we didn't overwrite the footer, so we're fine. And now what we're going to do is we're going to try and partition if it's necessary, which is indeed, now we need to do that. And so the size of this guy should change from 5D to something smaller, something like 20 bytes smaller. Yeah, 45. I'm willing to accept that. We checked that previously, right? So I'm not going to run through the numbers again. We know that the right block is not free, so then we skip this if. Then we set the new little guy that just spawned from our partition to be free. and then we reinsert it into the red-black tree. That's completely fine. And then we return the user section, the user pointer to that, and we should be able to, yes, perfect. So now we assert that the two are exactly the same, which should be correct. Oh. um, what happened? What's going on? So in memory, I see they are basically the same, right? Because these are the same 4 bytes, and then this is where the user section starts. Am I hallucinating? Okay, what is P1? P1 is A9C. A9C. So A9 and then C. And the pointer I'm returning to the user. Oh yeah, of course. I'm returning the wrong thing. So I think that whatever change I made, yeah, it shouldn't be P block. It shouldn't be the current block. It should be the previous block because that's now the new block. Perfect. So I assume, the Realloc behavior, we already took a look at it. At least that first call to Realloc. So I'm going to just say it's fine. So I think we can just skip it. Let's see. Let's run it. Yo, okay. We continue and we skip until here. And then we get to the Realloc part, right? Here. And then we should see these assert completely, pass with flying colors. Perfect. And now we free P3. Now, notice, oh wait, random hacker 89. I'm a long-time NeoVim user, and the only time I regret that is when I watch debugging sessions like this. Yeah, let's go. See, I want to try NeoVim eventually at some point in the future when I'm more skilled with my keyboard and I can actually take advantage of the shortcuts in the Vim motions. But that's interesting. I mean, I would think so. So does NeoVim just not have a plugin for like debugging visually? Or does it do, but maybe it doesn't have a memory inspector? I don't know, let me know. In the meantime, we're going to free P3, right? And what that means is we're going to have this first block, which ends over here, right? Rudifand, learning Vim motions is a life changer. Hi, by the way. Yeah. I use Neovim, by the way. Yeah. Wait, no, that's it's something I've heard from a lot of people, at least on the internet, right? Because like I don't, you know, some of my friends do not use Neovim and stuff like that, and like, but I've heard a lot about it, and it's the reason why I want to take a look at it to see like, what is the fuzz about? Why are they saying like, oh, Vim motion has changed my life. So eventually we'll discover that. I'll discover why this is a thing. But yeah, so that's it. Over here, I think we have a bit of an issue. No, okay. So we have 45, right? Which ends here because you can see the 44. Then we have the next block, which should represent the little tiny beat that remained after we performed the partition. And it ends over here at this 14. And then this 2E should be P3. So when we free P3, we should see this 17. Since these two guys are free, they should merge together. And this 17 should change to something greater, right? 2E plus 17 plus 4 bytes, if I remember correctly. 47, perfect, more than perfect. There are DAP plugins, DAP plugins, but they are nowhere as convenient as what you have here. I usually just run LLDB in a separate Tmux tab. Yeah, the emotions rock. What is a DAP plugin? What is the DAP? Wait, sorry if there are like basic things I don't know, but like, yeah. DAP is debug and adapter protocol. Oh, okay. But what does that like? What is debug and adapter protocol? Is it like extensions or plugins that interact with what the debugger is seeing. And so the debugger has a protocol to communicate that. So that's the protocol you use when you create your plugin, your plugin. Yeah, sorry. I imagine that is something like an LSP of sorts, like not an LSP, but like, there is a protocol for the two to communicate so that one asks the other another thing. Never heard of a DAP either. Sounds like LSP, but for debugger. We gave the exact same example at the exact same time. That's so funny. Yeah, exactly. So I don't know. Um, oh shoot. Oh shoot, I executed that line. I didn't want to. Okay, that's fine. Let me rerun it. It's exactly like LSP for debugger. Okay, that's perfect. I see. All right, that's perfect. I mean, let's see. Let's Realloc 2. Enter here. Okay, so what we've been doing is we are taking a look at, the exact same thing as always. And we already know that this first Realloc works, which is great, fire. Now we free P3 and we see the 17 change to a greater value, 47. And now we try to reallocate P2 now again to a section that is 110 bytes long. So we're going to enter this. And remember, so the mental picture you should have right now is, and I'm going to open the Excalitor for this, I know, is, let me go to the drawing we have. There you go. It's something like this, right? Where we have, let me erase this. There's too many drawings, people, too many drawings. We've been drawing a lot. So what you should see is this guy is P1, right? This guy is P2, 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 and this guy is P3. P3. Okay, perfect. And what we need to have in mind is, the stroke width, I need it smaller. What we need to have in mind is we first free P1, right? So they're all allocated. They're all occupied by some sort of information. We first free P1, and then we try to reallocate P2. The only place it can live is if we merge P1 and P2 to create a bigger block, and then write P2's information over here. So that's what you saw with the AA and the BB changing places. It was simply merging these two together and then making this entire block be allocated, right? So this is what we call P2 underscore, right? Because it's like the new version of P2. So this entire guy. And it's allocated too. Then after that, we free P3, right? So we free that block on the right. We free it. And then we try to reallocate P2 underscore to a bigger block of size 110. And what that's going to do is it's going to grab the, it's going to grab this block on the left and it's going to expand it to the right. So notice that there's something interesting here that I actually missed. And it's the fact that when we merge these two blocks together, we know that the size of the request is like 68, right? But this block is huge. It's like 92. And so we say, well, it would be a waste of space if I give to the user a block of size 92 when they actually only need 68, right? For that reason, what we do is we merge these two blocks together and then partition the block, which is what you saw about, block partitioning. We partition the block so that it is a little bit smaller and there's an extra bit over here. That extra bit is the 17 that you saw. Now, after that, we free P3. And when we free P3, P3 realizes, oh, I have a free block to my left. And so that ends up becoming, they merge together since the two are free blocks. So then, they see each other and they're like, oh, we can just create one big free block. And that's exactly what you see as the 47 right here, right? 47 that you cannot observe that 47 here that I'm pointing at with my mouse. That is this big block that was just generated, and that is free. So given that, we after we call realloc p2 underscore. I think I'm just gonna hide the camera for a second while this explanation goes on. Yeah. So while we have P2 in this free section, when we call realloc P2 to a block that's 110 wide, it's going to merge everything together, right? Everything. But this block is also huge because it's like 96 plus whatever this guy is, which is something like 120. It's gonna be a big number, right? It's gonna be something definitely bigger than 110. And thus we are expecting that after merging the two together, there's gonna be like a little block left on the right after we partition the blocks. So just have that picture in mind, and that's exactly the behavior we're going to be looking for here when we debug. Yeah, that's all. So let me put the camera now up. That's perfect. Now let's open the debugger. Okay. So what we're doing is when we enter this realloc, right, we align the size. So the size that they're asking for is 110. So we're probably going to align it to like 112 or something like that. 116. Okay. Because 116 plus 4 is 120, which is 8 byte aligned. So perfect. Then we calculate who the previous block is, which we have no previous block, which is correct, right? As you saw here. Oh, sorry. As you saw here, right? P2 underscore is the first block ever, so it shouldn't have a previous block, and that's exactly what happens. But it should have a next block, right? And that next block is block 96. We calculate the space needed, and we say, well, is the current block enough to host, the 116 bytes that we currently need? And the answer is no, because our block is currently of size 68. So we need to expand this by a lot. So we go to the expanding section and we say, well, is the block on the right free? And the answer is yes, it is free. So we should enter this if. Perfect. We remove the block from the red black tree. So we should see this being removed. And thus the root is now FFFFFFF, which means there is no root in the red black tree because now the red black tree is empty. There are no free blocks. Now we coalesce those two blocks. We merge the 45 block, which would be P2 underscore, with this 47 block, right? And so you should see this 45 become bigger, become something like 7D or 7C, something around that area. 8D, okay, yeah, kind of. Just this huge amalgamation of two blocks. And so now this is as wide as all of the states that we had before. So now we're going to partition if it's necessary, right? And in fact, let me verify that's the case, because we have 40, 40, and 40. That's 120. Plus the fact that each 40 needs to be 8 byte aligned, so it becomes a 44. So that 44 plus 4 is 8 byte aligned. So that's 44 times 3, which is 132, if I'm not mistaken. 132, and then you need to add the headers of each. So each one has a header of 4, and 4 times 3 is 12. So 132 plus 12 is 144. So in total, we have 144 bytes in a heap, and this block size is 140 plus the 4 bytes of its header, 144. So this block is now as big as the entire heap, which is what we saw here in the drawing. Now we merged the two blocks together, and now we need to say, well, actually that's too big, right? That's too big, and I think we can partition it. So we need to see that this right block becomes, okay, block 144, which is correct. And now notice that the size shrinked because we partitioned the block, and then whatever's remaining, that tiny bit, we leave as a free block. And thus, what we should see is, well, this guy is not null, right? We actually got a new free block. And so we need to set it to be free, and then we insert it into a red black tree, which should change the root to be something rather than FFFFFF, it should be 144. Yeah, 90 in hex. And so now we return that, we return the pointer to the new block, and then continue. Perfect. So now we assert that we actually didn't move at all, which is true. We didn't move the user's information. And the whole, this is a 40 byte long message, da 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 da, and then BB and then the exclamation marks are there, right? And now we should be able to, without our sanitizer complaining, write this message that is actually, I think it's 109 characters long, which adding the null terminator is 110 bytes long. Perfect. So it seems like it worked, and in fact we see the message. This is a 40 byte long message. Never mind, it's actually 110, or I think, happy face, not terminator. Okay. So perfect, it seems like it works. And this is the place where the block ends, and finally we return true to say that, yes, we have finished the test. Okay, it seems like Realloc is working. We have not tested all of it, but we have like a good enough degree of confidence, right? I think. So that's great. I think so currently what branch are we in? I think this deserves a prize. The fact that at least those two tests pass. And the prize is pushing it to the GitHub. So let's do something like git commit, and then there's gonna be test, and it's gonna be a test for Realloc. Add basic Realloc tests. I'm gonna call them inspection tests because notice that we have a problem, right? When we execute the tests, these are like kind of tests, but kind of not. And the reason why I mentioned that is because when we run the test, we ourselves are the ones that verify correctness. Right? We take a look at the heap and we see, does this make sense? Right? Are the blocks moving in the right direction, and etc. The program doesn't really check that at all. So if you were to run this, it would run, but it doesn't check for correctness per se. Right? We are the ones in charge of that. So these are more like inspection tests, or like little scenarios where you can go to the memory inspector and take a look at how the things are moving and verify that everything is working. So given this magical feat, right? Ooh, Goose Speed 35, welcome to the chat. Wondering, the allocator you're going to develop, what is the target you would like to improve or solve? So currently, I think there are many memory allocators out there, and I think it would be a little unrealistic for me to pretend that I can do a better job with like something as, like, say, JMalloc, right? The reason why we're doing is encoding a memory allocator from scratch is just to learn. It's to learn about memory allocators. I knew nothing about them before starting this, and I just wanted to know about them. I just wanted to know about what a memory allocator is, how it works, what to do. So this is just for the sake of learning. Yeah, if that answers your question. And yeah, and actually, it's we are basically finished. I would say, like, not basically finished. I know, guys, but like, we are like platonically like finished. It's like the idea is there. We've written all of the code. We've ran some tests, and it seems like it works. Now we just need to make that process automatic so that we can develop some tests. We can just run them and say, yes, this guy is correct. Right? So yeah, that's what we aspire to sort of build. Shouts at Fantasy Studio, welcome to chat. I saw someone else enjoying the pain of memory allocators and came to share my software. Yo, let's go. Let's go. And thank you for following, by the way. So do you mean like you're also developing a memory allocator? Or you have developed one in the past? It seems very Very good. Um, and actually, you guys' experience, because I've said it quite a lot of times, many of the people in my chat I've noticed are like very experienced programmers. So you guys maybe can help with this. And we need to think of our interface when it comes to testing. Like, how are we going to perform the automatic testing for our memory allocator? Because currently, once again, we have inspection tests, but not actual automatic tests. And I think it's something important, like to dedicate some thought to, mainly because, take a look, like, right, we thought about it for a red black tree and we ended up determining like these functions, create block, that make it very easy to sort of read what the test is doing, right? It's creating a red black tree, is inserting something, and then assert that the red black tree is equal to the vector representation of the red black tree. So it's like easy to test things. If I want to create a red black tree and test that it is equal to what I think it should be, I just grab the expected tree and write down its pre-order traversal representation, and then the test is able to run. So I want to do something like that sort of interface where you can just write tests very easily is something that should be ideal for us. So we need to sort of determine how we're going to achieve that. Like, what are we going to do in order to get that? I see new messages in the chat. Let's see. Memory allocators related to game dev. Ooh, mainly for multi-threading physics. If you use Unity, you can actually write your own allocators and inject them into native code with unmatched data structs. Really? Don't know. Unity gave you that freedom. Basically, a memory allocator for box 2D 3.1 with physics contact solving. Wow. And what does it? So why do you need a memory allocator? Like, not why do you need a memory allocator? Like, of course you need one, but is there a specific feat or like feature or thing that needed to change that forced you or like motivated you to say like, yeah, we need a custom allocator for this? Because this one's for learning, right? So there's nothing that's been introduced, right? I imagine if you did it for your project, then it probably had to do with something, something better where you're like, oh, we need, no, there's too many boxes, so then we need to, merge them together and we need to compact the heap and do a bunch of stuff. I don't know. Tim MXN. Yo, thank you for following. Let's go. um, we actually, guys, we've grown 130 followers, 32 actually, which is absolutely insane. I don't know. Like 2 weeks ago, we had 10. So imagine. Um, anyways, I digress. But so right now we need to sort of create the testing interface. So people, we have 30 engineers looking at this. How are we supposed to test our memory allocator? So I'll give you some of the things that come to mind, just to let me. Oh wait, we can first read the message. The feature involves a lot of fragmentation on collisions, where each fragment can shatter off and is held in memory with its own set of possible contacts. Imagine freezing water and then shattering it, and each piece of ice can do physics contact. I see. Interesting. Very interesting. That's perfect. And yeah, sounds pretty. Think of a game like Noita, where every pixel has physics simulation with good performance and memory usage. I don't know about Noita. I don't know what Noita is. Sorry, I don't know. Let's look it up. I just want to know what you're talking about. Noita. Oh, so is it like every single pixel? It's like those where you can create like caves, and like the world can be modified by whatever you do. Like you can carve into the ground, and the hole is gonna stay there. Um, I see. So that's the type of game you're aiming for. Then it's pretty good. Pretty good. What is the plot of Noita? Is a single-player video game in which the player character is a witch who finds, collects, and casts spells in a procedurally generated 2D world where every pixel is physically simulated. That's absolutely insane. Every pixel. The amount of performance, like optimizations that I imagine you would need to perform is absolutely insane. Damn. Okay, yeah. Like, as I've said it before, most of the legendary programs come from game development, and there's a reason for that. Now, basically, it is a game where every pixel of anything has physics simulation and can do chemical reactions, even like acid, ignition, gas to liquid state, and so forth. That's incredible. Every pixel? Like, yeah, that's kind of insane. You ask me. Wow, pretty good. Yeah. Right. So I'll take a pause for now and let's really think about what we need to do for the automatic testing. So I'll tell you what I'm thinking about right now, and you guys can give me better ideas, right? So there is a sense in which we would want to test our implementation fully. And by that, I mean test that every single byte is in the correct position, test that, all of the information is there, and etc. But automatically testing whether or not every byte is in the correct position, it seems to me it is equivalent to testing or sort of to re-implementing the memory allocator. Because if you're able to retrace your steps like byte by byte, then it means you're basically running the program. And so it seems to me that like that is a little bit unfeasible unless we manually sort of touch every single byte. In which case it wouldn't be like, I guess it would be automatic, but it would be very prone to, regression mistakes where, or not regression mistakes, right? But like regression or like some sort of invalidation. So if we decide, for example, that color should now, instead of living in the size field, living in the parent field, then the bytes are just in a different position and we're going to fail that test entirely. So that is not what we want. We want something that is a little bit more coarse, like, it's a little bit not too fine grained. Want something that's a little bit broader. So what I'm thinking is we could create this sort of set of functions or set of stuff where we take a look at something like, expect block here. And then we provide a pointer to it. And then it just verifies that there is a block of the size that we specify with the information that we specify, right? Doesn't really care that much about the metadata. It just cares that the size is the same, that everything is the same, right? And that should be able to work, I hope. Because then we can say, expect a block here, expect a block here, and expect a block here. And I just need to say, expect it to be allocated or free, and expect it to have this much size. And that's all. So I think it would be reasonable enough, question mark. My only problem with that is that when we try to specify sizes, remember that the memory allocator, like, changes that and it like, the memory allocator like changes that and aligns the size to be like 8-byte aligned. And so it is like sometimes a little more difficult, right? Because so for example, remember that here we said realloc to a block of size 65, but the allocator actually gave us a block of size 68, and that's to comply with the 8-byte alignment. So kind of for the same reason, if we test something like, expect block in position P2 to be of size like 65, then this would fail, right? Because the block is actually not 65, it's 68. So maybe we can do like a line and then actually align it, or maybe all of the sizes that we pass are already aligned. Not sure. So we would have to see, right? Um, okay, let me read. My 2 cents. For testing your implementation, you may take a look at Valgrind, address sanitizer, etc. for performance. You may check memalloc bench. Ooh, okay. Wait. So when you mention we may take a look at Valgrind, address sanitizer, etc. Yes, but like we also want to test like the behavior per se, right? We want to, because like is Valgrind able to do this? What I mean is, in this example, right? For example, a little bit redundant. Like we allocate 3 blocks, and notice that every single thing that happens in those 3 blocks. So everything happens within the heap. But we want to check the correctness of that. So rather than checking for memory leaks or like maybe we write a byte that we haven't yet allocated, um, we need to check that like the behavior inside it, that this block is indeed merging with this other block, and that this block is indeed being moved around to a different place and so on. And that's what has me a little bit puzzled. I think the performance thing that you mentioned, that is very helpful. Me malloc bench. You may take a look at that. I don't know what it is, but it sounds like exactly what we need to measure performance. I think our memory allocator is not very performant, so we would have to also change that. Um, we need to perform a lot of tweaks to a memory allocator because I imagine it's really inefficient right now. Um, let's see. Suite for benchmarking malloc implementations. This is awesome. This is exactly what we need. Wait. Let's. I want to bookmark this. Yo, let's go. Thank you very much, Goospeed. This is exactly what we need. Suite for benchmarking malloc implementations originally developed for benchmarking memalloc. Actually, what is memalloc? Oh, is this a? Oh, I remember somebody sharing this in the chat, and then I said, "Oh, I don't want to, I don't want to take a look at the code because I don't want to bias myself." Yeah. Okay. I see. So this is the memalloc bench. It's quite easy to add new benchmarks and allocator implementations. Please do so. Enjoy, Dan. Perfect. All right, I think we can use memalloc bench, and that's actually I feel like it would be exactly what we want. Let's see. Strignit 3. Oh, Strignit! Yo, welcome back. We haven't seen Strignit in like 7 days or something like that. Welcome back. Maybe you can go with, for example, fuzzing plus a bunch of assertions. What is fuzzing? I've heard of memory fuzzing, like the name, but it's not quite clear to me what it is. So memory fuzzing, fuzzing, memory fuzzing. What is it? It's like, so let's see, fuzzing. Is it like something that automatically changes bits around to see if, let's see. In programming and software development, fuzzing or fuzz testing is an automated software testing technique that involves providing invalid, unexpected, or random data as inputs to a computer program. The program is then monitored for exceptions such as crashes, failing built-in code assertions, or potential memory leaks. Typically, fuzzers are used to test programs that take structured inputs. The structure is specified, such as in a file format or protocol, and distinguishes valid from invalid input. An effective fuzzer generates semi-valid inputs that are valid enough in that they are not directly rejected by the parser, but do create unexpected behaviors deeper in the program and are valid enough to expose corner cases that have not been properly dealt with. For the purpose of security, input that crosses a trust boundary is often the most useful. For example, it is more important to fuzz code that handles a file uploaded by any user than it is to fuzz the code that passes a configuration file that is accessible only to a privileged user. Interesting. So the fuzzer just like goes around, tries to generate chaos, flips bits around, gives it to you, and checks that you actually rejected when you should. I see, I see. Jab1, thank you for following. Yo. Um, Shatter Fantasy can't stay sadly. Wish you luck and enjoy. Yo, good luck, Shatter Fantasy Studios. Thank you for hanging around. SackJ Dev. Hey, context? Okay. So currently we are developing our memory allocator, and we have already written malloc, free, and realloc, and we're just trying to find a way to sort of more to test it more rigorously, right? Because currently we've just been inspecting our memory and seeing like, yeah, you know, I think it works. Like, so I think I would like to be introduced to a sort of more formal testing where we actually run tests and they automatically tell us whether something is good or not. You can look at fuzz test for C++. Bit of a pain setting it up without CMake though. Hello, yay. Root infant. Root Rootifant. Okay. The ultimate confidence test would be to take a real program which uses malloc and free and replace the libc version with your own. Zig has built-in fuzzing in tests, which is quite handy. Wait, that's pretty cool. I didn't know Zig had that. Yeah, and I agree, Rootifant. Like a real test would be go to some sort of, go to Firefox, right? And, record what the allocations are and then run those allocations again or something like that. Well, of course not, maybe not Firefox, right? But like some other program, and so on. But that would be like, I feel that would be like at the end of things, right? Right? Like not at the end of things, but at a moment where we've run enough tests where we say, yes, this should be ready. Like for now, we want something that allows us to do it automatically. So um, I think, because what is my fear? My fear is the fact that if I understand the fuzzer correctly, I'm like, once again, I just got introduced to this concept like, 2 minutes ago. If the fuzzer just flips like random bits, then it's possible that it also flips the bits for, say, the size of a block, right? In which case, like the program functions based on the assumption that like nobody's going to modify the size bits. Of course, the user could technically, since we give to them a pointer, just go back like 4 bytes and overwrite that information. But currently, like, I'm not trying to test or make an allocator that is secure, or that like, that it's like, oh, the user's stupid and then it's possible that they override the information. Currently, we're more focused on like creating an actual allocator and seeing that it works and then invest our time maybe on creating all of these protections so that the user doesn't override anything and stuff like that. You can use a puzzle to generate random input with some constraints. Oh, so it's also constrained. Interesting. No, just create a lib with your code and do ld preload your lib there, chromium or so. Yeah. So something like that is what I'm saying, but I feel that's like at the end of things. Right? When we're like decently sure that the memory allocator is like doing what it's supposed to. Because currently we just ran this. We just ran this little program. We were like, nah, it works. Yeah. So hopefully we can do a little bit of a better job. And what I mean by that is like, the main idea that comes to mind is sort of doing these manual tests, yes, but like make them automatic in that when you run them, yeah, right, the output is exactly what it's supposed to be. But yeah, first do some unit tests. Okay, yeah, exactly. So I want to do the unit test. So as I mentioned, I think the idea is, or like the idea I have in mind is write a function, something like expect block, right? Expect block and then pass a pointer to it on where the block is supposed to live and what the size of that block is supposed to be. and how many, whether or not it's free, right? And then as we go here, and then we say, oh, okay, right, we're testing malloc. I just allocated a new block. So then what I say is something like expect block at A1 that is of size 23, and it's actually allocated, right? And then I can go maybe to the free tests, and then I say, okay, over here, expect that the block that's represented by P3 has size, 52, and then it's actually allocated. And then after we free, expect that same block to be free, right? So stuff like this. I think we just introduce some sort of function like this that just allows us to test that the blocks are in the position they're supposed to be. And yeah, and something like, expect this thing to be, invalid, right? This block is no longer, etc., etc., etc. I think that's what I would like to do, something like that. Random Hacker says, have you considered adding something like Unity to facilitate test writing process? What is Unity? Like, is Unity like Unity C? I imagine I can just, well, of course it's gonna show me the, maybe we can do tests. Unity is a unit testing framework written in 100% pure ANSI C. What is this? It's been carefully written and self-tested to be portable, work efficiently on tiny 8-bit microcontrollers to 64-bit powerhouses. As a single C file and a pair of header files, Unity provides a slim but expressive collection of assertions and supporting structure, enabling you to write powerful unit tests. Interesting. So I know the only thing I know of is Google Test, I think is the name. Google Test. Google Test. Oh, but it's in C for C++. I mean, every C file can be interpreted as a C++ file, so maybe we can just get away with that. But yeah, so what is the difference between Google Test and Unity? Because I've used Google Test once. I'm just not very experienced. I'm just not too experienced with like testing and stuff. Like all of the projects I've developed are like personal projects and so, right? Unity is one of the simplest and easiest to set up options as it's just a single header. Okay, so we discard Google Test. It's too much for what we want. Unity is better. Okay, yo, let's go get Unity. Okay, I'm just gonna trust you guys to be honest. Yeah. Download an official release probably. If only GitHub had a download button. Okay, so source code. Imagine I just download a zip and it's gonna have one file, hopefully. So Unity 2.7.0. And then, whoa, there's a lot of files. Which one of them should I write? We all said that sentence. If only you know had a download button. Yeah. Um Let's see. So let me actually read because I didn't read. How you get Unity depends on how you plan to use it. Unity at its core is just a C file and a couple headers, but there are also optional feature files, support scripts, etc. Unity is meant to be built into a test executable for each unit. That means something needs to manage those builds. If that build management is going to be seedling, you've nothing to worry. What is seedling? Okay, installing a seedling will automatically install Unity. Otherwise, you're going to want to grab the source. Okay. um, guys, what do we do? Guys, you said there was only a C file. So do I just need to grab these two? Uh, okay, so this is where you see my inexperience shine. I like I don't know how to write a CMake file, right? I don't know how to write a make file. Um, there's like many things I don't know that are like very fundamental that I should actually learn. Ooh, this is a little bit of a weird choice of a background, but it's okay. um, oh, I want to see what it looks like. So it has a header file that looks like this. Then we make a test file which checks for some basic things like rollovers and whatnot. Test assert equal hex 8. Oh, seems like it's pretty decent. Okay. Um. Oh, Smart as 42. Welcome to this stream. What is this memory allocator you speak of? Are you inventing new assembly of some sort? No, not really. The memory allocator is just a memory allocator that we wrote in C. We are finished with our implementation almost, and now we're just trying to find a way to test it. So we wrote malloc, free, and realloc, right? And then we have the test file. And we're trying to download a unit testing framework that chat has suggested. So let's see. You basically just copy the SSC to a vendor folder. Oh wait, sorry. No CMake. They don't know web UI. They don't know web UI apparently. You basically just copy the SSC to a vendor folder in your project or something, but you have to write a make file though. So don't worry, everyone flows in basic stuff. Okay. Yeah, no. So you know, I'm going to prepare myself. I'm going to grab one day. And I'm just gonna learn all I can about CMake and make files, and then actually come back to the stream and be like, guys, guess what happened yesterday? Guess what happened yesterday? I'm not an expert on CMake files. Start creating the most verbose building system and unnecessary commands. But yeah, no. For now, I think I'm gonna follow intuition and what you guys are saying. So you're saying random hacker, you basically just copy the SSC to a vendor folder in your project or something, but you have to write a make file now. So I imagine that maybe what we have to do is, so if we do something like external, right? Or should I call it vendor instead? So I don't know what the naming convention is. I think I'm gonna follow your recommendation to call it a vendor. Is it seen? Oh wait, it's the same logo, so either meaning works. It's fine. So it's called a vendor, and then maybe I can create something like Unity, perhaps. Unity. It gives you the Unity logo, which is funny, but yeah. So then we're gonna vendor Unity. I imagine. Let me go to workspace number 3 and bring that to workspace number 1. There you go. Oh, sorry, no, this is not the guy I meant to bring back. I meant to bring this guy into number 1. There you go. So now we could copy the source folder, copy this, and then paste it over the vendor folder. Paste. Hello? Oh, I don't think I can do this. I think if I just drag it, it's gonna be fine. Yeah, perfect. Okay, I imagine that mess on the build is not. I'm just gonna delete this because I'm pretty sure I don't know how to use it, so it's better if we just write from scratch. So okay, these are all the stuff. This is the source code. I imagine these are the files I need. Oh my god. Whoa. Okay, that's a huge header file. Never seen a header file like that. It's also not like I use external libraries or stuff. So now what I imagine we need to do would be so let's see. I imagine that we need to do something like a cmake lists.txt, something like that. And then we would need to do I don't know, project or like set to project. It was something like that. And then we set the name and all of that stuff. And then once that's done, we create a cmake file here that makes this into a little library. And then we're able to import it from everywhere else. Can I just not add this to my compilation and then just say something like, GCC and then just add the unity.c in there. It would be very annoying, I imagine. A simple makefile will do. It's much easier than CMake unless you're very comfortable with CMake. Yeah, I'm not very comfortable with CMake. I've seen it though, but so let's see, makefile. The problem is, okay, you guys are gonna have to be, uh, this is gonna be a rage baiting session because I'm going to start doing stuff and you're gonna be like, no, no, that's not how it goes. So, you're ruining everything. And then, yeah, it's gonna be a little, oh, make file tutorial by example. Wait, we may have found it. Okay, why do make files exist? Well, we sort of know, we know the reason. But okay, running the example. So hello, echo, hello world. Okay. So to run these examples, you need a terminal. Let's start with the simplest of makefiles. Here's the output of running the above example. Perfect. Then we have a makefile syntax. So a makefile consists of a set of rules. A rule generally looks like this. So we have targets, which are prereqs. Then we have commands. Okay, the targets are file names separated by spaces. Typically, there's only one per rule. The commands are a series of steps typically used to make the targets. These need to start with a tab character, not spaces. So, okay, now I am very confused. The targets are file names separated by spaces, and the commands create the targets. So, okay, sure. The prerequisites. Oh, so targets is different. Yeah, targets is different from prereqs. Okay. The prerequisites are also file names separated by spaces. These files need to exist before the commands for the target are run. These are also called dependencies. The essence of CMake. So let's start with a hello world example. Okay, so when you say make hello, it executes these series of commands and it checks that the prereqs that you specified are there so that the commands can run. Okay. We'll then run make hello, sure. It's important to realize that I'm talking about hello as both a target and a file. That's because the two are directly tied together. Typically when a target is run, aka when the command of a target are run, the commands will create a file with the same name as the target, and here's the hello target does not create the hello file. Let's create a more typical make file, one that compiles a single C file. But before we do, make a file called blah.c that has the following contents. Okay, so you have this. Then we create a make file called this. So if I do make blah, it's just gonna execute this command. This time, try simply running make. Since there's no target supplied as an argument to the make command, the first target is run. Interesting. There's only one target, and so it just runs it. Blah will be created. Okay, I see. But there is a problem. If we modify blah.c and then run make, nothing gets recompiled. We solve this by adding a prereq. Yeah, okay, when we run make again, the following set of steps happens. Okay, this last step is critical in this essence of make. Okay, make decides if it should run the blah target. It will only run if blah doesn't exist or blah.c is newer than blah. Okay, what it's attempting to do is decide if the prerequisites of blah have changed. Yes, of course. To make this happen, it uses the file system timestamps, I imagine. Make sure that you understand this. It's the crux of makefiles and might take you a few minutes to properly understand. I think we understood it already. You could, for example, modify a file and then change the modify timestamp on that file to something old. If you did, make would yeah. More quick examples. Let's see. The following makefile ultimately runs all three targets when you run make in the terminal. It will build a program called blah in a series of steps. So selects the target blah. Blah requires blah.o, so make searches for the blah.o target. It requires blah.c, so make searches for the blah.c target. Blah.c has no dependencies, so the echo command is run. Okay, then it's run this command because all of the blah dependencies are finished. The top cc command is run because all the blah dependencies are finished. Okay, that makes sense. So whenever it doesn't find a target, so these prerequisites are not only files but also targets. Okay, so it interprets it first as a target, and then it goes find if there's a rule for it, and then it runs it. And if it doesn't exist, then it tries to find it as a file. It seems. Okay. Okay, I see, I see. If you delete val.c, all 3 targets will be rerun. If you edit it and thus change the timestamp, yeah. This next example doesn't do anything new, but it's nonetheless a good additional example. It will always run both targets because some file depends on other file, which is never created. So some file other file echo, this will always run and run second, touch some file. Okay, I see. Make clean is often used as a target that removes the output of other targets, but it is not special work in make. You can run make and make clean on this to create and delete some file. Know that clean is doing 2 new things here. It's a target that is not first and not a prerequisite. That means it'll never run unless you explicitly call make clean. It's not intended to be a file name. If you happen to have a file named clean, this target won't run, which is not what we want. See .phony later in this tutorial on how to fix this. Okay, so we can have variables in make too, it seems. Variables can only be strings. You'll typically want to use this, but this other guy also works. Here's an example of using variables. So we could create files and then put them together, and then we can replace it. Okay, that makes sense. Single double quotes have no meaning to make. They are simply characters that are assigned to the variable. Quotes are useful to shell bash though, and you need them in commands like printf. In this example, the 2 commands behave the same. Okay, so variables are defined by the new lines, and I imagine that the pound is useful for comment. Reference variables using either these. Okay. Targets, the alt target. Making multiple targets and you want to run them all. Make an alt target. Okay. Perfect. Multiple targets. Sure. When there are multiple targets for a rule, okay, the commands will be run for each target. I see. $@ is an automatic variable that contains the target name. Interesting. So when we run all, we first run this guy. It tries to look for it. It finds it. It executes this, and so it echoes f1.0, and then it tries to find this guy, and then runs it, and then runs it. Okay. Automatic variables and wildcards. So both asterisk and percent are called wildcards in make, but they mean entirely different things. Asterisk searches your file system for matching file names. Okay. I suggest that you always wrap it in the wildcard function because otherwise you may fall into a common pitfall described below. Okay. So this print target depends on every single C file. I see, I see. And then it runs this command for every, well, not every such file, right? It only does it once. So what is this $? We'll see. Asterisk may be used in the target, prerequisites, or in the wildcard function. So danger. Asterisk may not be directly used in the variable definition. Danger. When asterisk matches no files, it is left as it is, unless run with the wildcard function. Ooh, okay. I see, I see, I see. LA profit? What do you mean? Huh? What do you mean profit? ls-LA. Did I solve the question? What question? Oh, this guy? The question mark? Because I know the at represents the current name of the target. So if it was an at, then it'd surely be for him. Oh, you're joking? Okay. I was like, wait, no. Okay, wait. I'm missing something if that's the case. Okay, I see. So thing wrong, thing right, sure. The percent wildcard. So how does it work? It means it will pass every match of the wildcard to the command. Oh, okay. So it just lists all of the things that it found, or does it run the command for everything that it found? I think it just lists it. Yeah. Okay, yeah, it lists it. Okay, perfect. Wildcard is really useful, but it's somewhat confusing because of the variety of situations it can be used in. When used in matching mode, it matches one or more characters in a string. This match is called the stem. When used in replacing mode, it takes the stem that was matched and replaces that in a string. Percent is most often used in a rule definitions and in some specific functions. Okay, so automatic variables. There are many automatic variables, but often only a few show up. So this guy would output hey, yeah, the target name. Outputs all prerequisites newer than the target. I see. Outputs all prerequisites. It outputs the first prerequisite. Okay, I see, I see. Fancy rules. I think we can stop reading from here, because if these are fancy rules, probably I won't need them. And I mention it because, you know, the article is really long. And like, I'll read this on my own time, but maybe not on stream since it's like boring, given that you guys already know about it. So, all right, given the knowledge we've collected, all right, don't spoil anything. Don't tell me what to write. Okay, I want to run an experiment. I read Makefile for the first time, and we're just gonna run with whatever knowledge we acquired. So I imagine that we create an all. Then I'm gonna try to create a target here, which I imagine will be the test for the memory. And we depend on memlibc. We also depend on mmtest, of course, .c. We depend on mmc, and we depend on, not the arbitrary test, but we do depend on the Realloc tree file. Do we depend on anything else? No, not for now. Nonetheless, we have a to-do because we also need to, you know, sort of like use Unity somehow. I want to first create the makefile for the things that we have already, and then implement the Unity thing. So we have mmtest, right? mmtest, and mmtest is just depending on this stuff. Don't think there's anything else. Okay, perfect. And so what we would need to run would be gcc, and then we're going to do, you know, memlib.c. And actually, yeah, I saw what you were saying. Well, actually, we can just use this guy. Okay. Anyways, so GCC that guy, and then we output into mmtest, which would be the name of the little guy, and then we output with debugging flags. I imagine that we could just include a variable, something like flags, and then just say that like -g, right? The -g, whether or not we want debugging. So we could include it. Well, I imagine that it's better to include the flags. Is it better to include the flags in the beginning or at the end? I include it at the end. And then I can reference flags over here, right? I think so. I think this is fine. And so if I do this, we would be able to do this, right? And inside of all, I just include mmtest. And this would be a normal, sorry, I don't know why I deleted the to do. I'm just gonna put it up here. This would be a normal make file. I think so, right? So now if I just go and just run make, okay, mmtest has a problem. This non-void function. Oh, I just yeah. This was a joke. I didn't want to write that actually. Well, it was not a joke. It was just like a proof of concept, if you will. Let me just Control Z into it. Perfect. And I think it created the files, right? Yeah, we created mmtest. And now if I just run mmtest, okay, perfect, it works. So it seems like yeah. So it costs my brain. GCC profit goes up. Is this the way you remember what how to write the GCC? Okay. Output profits at flags.com. All of these mnemonics just to remember the make file. Okay, that is actually how my dumb brain remembers thing. I keep remembering that 4 bytes is a nibble because nibble also like brother. Okay, brother. Okay. Anyways, so I think this is the way we do it, right? So test and all of that. So now how do we compile Unity? I imagine if I do something like Unity, maybe I can create that target. And then the way we compile Unity is the same question mark. So all I need to do is unity.c and then say GCC profit goes up, output, and then add, and then we include the flags that we want. Although we don't really want to do that for Unity. We want the flags to correspond to a program, and so we do this, right? And that should be fine, I guess. It's not really in Unity.c. It's actually in vendor slash unity slash slc slash unity.c. There you go. And then I imagine I include a dot slash or something. Will it get confused if I don't include a dot slash? I see sometimes programs get confused if you like specify folders like this. You gotta start with like dot slash. Because I don't know. Maybe it grabs like something else. I don't know. Let's try it this way. I imagine that like if we want to be fancy, I guess we can, create a Unity directory and then do something like vendor then slash Unity and that's it, right? Actually, not a Unity directory, but like a vendor directory is better. Then we call it vendor, and then we do this. Is this valid? Do we want to do this? Actually, no, this is really bad. This is like giving into the world of abstractions, of unnecessary abstractions. Perfect. So we do this, right? Perfect. Does MM stand for memory manager? Yeah. We just, it's like a random name. You just put it to differentiate it from the actual malloc and the actual free and the actual allocator. But yeah, so I think this is the way to, once Unity is done, we would require Unity, but not the file. Instead, we require the rule, right? The Unity like target. And then we can include that in here. Well, actually, not really, right? So Unity is already compiled. So I cannot include it into my C files. So should I instead include the Unity C file? Or do I have to, or am I able to just attach something that's already compiled into, okay, a little bit more of an experience here. You can use the -i compiler flag. Why would I want -i? Which includes the headers folder. Wait. What do you mean? What do you mean? Like use it for the vendor Unity SLC? Because I imagine, okay, yeah, I think you're right, because when this, well, unless I compile Unity and then there's some way I can use it here, but I don't think that's the case. Okay, so I imagine that this rule is just useless, right? And then instead I just do -i, and then I include vendor slash vendor. I just include vendor. And then I call things. Actually, no, I cannot do that. I would have to do this, right? So that unity.c is still able to include unity.h when everything compiles. And I'm able to do the same. Right, and then I include something like vendor slash unity slash slc slash unity.c. Is this the way? I think. Let's try. Nothing to be done for all. Brother, make it clear. Oh. Is there a make reset? How do I clear the cache? Wait, make that's just clear. Um, make 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 reset. Okay, yeah. Clean. Yeah, no, but like clean would get rid of all my files and like the files that have been created. I mean, like, how do I erase the cache so that it doesn't cache the fact that this target has already been created? Uh, uh, okay. I think if we just we should implement the clean. So rmrf, and then we're just gonna delete whatever we created, which would be test, right? Um, test, and what else? Nothing else, right? Yeah. So if I run make clean, I'll get rid of it. Then if I run make test, ouch. Okay. Um. Well. Well. Symbol not found for architecture ARM 64. Okay, what's happening? It seems like there's a problem. Where do we have the whole... Oh, where's the problem? Does the Unity thing compile alone? Well, I included it into my files, and then I included the header files that it has. So they all compile together as like one happy family. But yeah, so am I supposed to compile the Unity T alone, include the header files, and so that I'm able to reference the header files, and then just sort of link the object file over here? Is that a thing? Like, am I able to just do that? I have no idea. I'm also thinking through it. Okay. At least it's two. It's two of us now. Let me try and do that. Let me try and do that actually. Unity /src /unity.c. And then I can just run gcc and then bring in anything you have. And -o dash this guy. And then I'm going to include the vendor folder. So vendor /unity /src /unity.c. I think that's enough, right? Yes. So if I run that, if I run make unity, missing separator, stop. Oh, I accidentally included a line here. Shouldn't have been there. Let's see, make unity. Ooh. It's profit goes up. Yeah, it's not up goes profit. Okay. Make unity. Okay. Main reference from initial undefined. Setup is not there. Teardown is not there. Oh no. Oh no. Never though, looking at someone struggle with making is fun to watch. Okay. Okay. Alright, brother. Then that's like psychopathic behavior. I enjoy seeing other people suffer. Anyways. Let's see. So what do we, because Unity, and then if we, brother, are we just not supposed to compile the Unity thing by itself? What's going on? Okay, did I import the right files? That may be the other issue. Right? Like maybe let me open Finder. And then let me open here and then downloads. And then Okay, so SLC should be the only thing we need because the rest are tests, platform IO build, examples, auto, readme. Yeah, this should be the only thing we need. I want to take a look at what this meson build is. Maybe it has the exact instructions on how we should be able to reach this. Unity Inc. include directories dot then the source. If not, meson is the project unity.h. Brother, it's doing exactly what we've been doing. What? What are we supposed to do? Oh, wait. Okay. We're including the directory of Unity. Then we are compiling Unity and we're outputting it to an object file with the same name. But then, and look at this monstrosity. We are somehow calling some random function called underscore Unity default test run. And it's just not there. So I think that doing it, we don't want to leave Unity alone. We want to give it a happy family. By that I mean we want to compile it with the rest of things. And then after that, it's not gonna feel lonely. It's gonna feel happy and it's gonna give us what we want. Yeah, never mind. So what is it? Do I include the dot slash? Maybe that's an issue. Who knows? No. Do I need to include it in some sort of header file? And that will change things around? Sorry. Unity.h. Yeah, so VS Code is recognizing what the make file is doing. Oh, never mind. Well, I think I can go to. They have like a. Oh, they don't. Okay. Yeah. Guys, what are we supposed to do? How am I supposed to use Unity if it doesn't work? No. Okay. Do I just do this? Do I just copy the files and I put them in the outside folder? I move them out. I erase the vendor folder. And then I just, I just say compile with Unity 2. And then everyone will be happy. Oh, I thought it was gonna work for a second. Yeah, welcome to another one of the software enigmas. It shouldn't be so difficult to include a file in your project. Brother, what's going on? No. Okay, I think we're gonna have to go for the rudimentary approach. And I'm just gonna have to look for wait, no, move this to workspace 3. Oh, sorry, I moved the editor to workspace 3. Yeah, there you go. Okay. So now if we do how to include Unity tests. Well, I guess Unity test framework in my C project. And then somebody in Stack Overflow probably, yo, Medium, let's go. Okay. There's always hope at the end of the road. There's always a Medium post. Okay, unit testing in C is not very common for various reasons, including limited tooling and frameworks. Yes, perfect. Introduction to Unity. We already read what Unity was. No, thank you. No, thank you. Add Unity to a C code base. So traditional makefile for building. If you want to fully understand the makefile and its workings, yeah. So we built for the project build files, the project source code, the project test files. Unity is the Unity source code. Writing a simple calculator. Sure. Yeah, I don't. I want to take a look at this. Yes, okay. Basic unit test file skeleton. So we include unity.h, and that should be, ooh. Oh, am I supposed to include these functions? Is that why it's complaining? So it's actually working, but it's just complaining because I didn't create these functions? Oh, we defined two functions setup and teardown before and after the tests. Are mandatory and allows to set up any necessary test case conditions. Oh, wait. Had I read the documentation, then we make a test file, we check some basic stuff. Nothing to do yet, nothing to do. Okay. It's fine, it's fine, it's fine. Okay, that means we were in the correct path. Kinda. Almost. I don't know. Anyways, we include unity.h, and that means that we're able to create the teardown and that, yeah. Void setup, and then void teardown, teardown, teardown. There you go. Except when the medium post is locked behind a paywall. Yeah, it's unfortunate. It's unfortunate when they are. But for now, I don't think we need to do anything for the setup or the teardown, right? And then we need to include inside of main unity begin and then return unity.end. Okay, I'm just gonna copy this because we're gonna have the exact same structure. And I first want to duplicate this file, so I'm gonna copy it and then paste it again. And just like preserve a copy of a file before we implemented all of the unit testing and stuff. Okay, perfect. So now, actually, now that I think about it, what branch are we in? We're in Realloc. Okay, let me check out the main. And, test. Okay, I guess so. Git add test. T, and then we commit. Oh, actually, yeah, sure. Test Realloc. Modifications. Well, what did we do? We added nothing, right? What did we add to the test file? Oh, we added Unity and this stuff. Yeah. Before that happens, yeah, we should have no changes. So we should be able to check out main. Yeah, perfect. And then what we want to do is we want to merge. I think it was what was the name of the branch again? Git branch. Then we want to feed Realloc. Okay, git merge feed Realloc. Perfect. And then we want to create git checkout. That should be another branch that's called test. Yeah. Introduce unit tests. Something like that, right? So now we're in that branch, and now we can actually, now we can actually do stuff. So I think that everything worked when I had it in the vendor folder. It's just that it was incorrect. Unity. And I just paste in the src. There you go. So these files can go there. So we just move them. Great. Okay, and now what we do is we modify the makefile first to include, vendor slash unity slash ssc slash unity.c, and then we include that guy. Perfect. Okay, so now what we want to do is we want to include all of this stuff. So we want to actually include the unity.h, which is not picked up by the extension, which I think can be solved by going into the configurations, if I remember correctly. And then there's something called the include paths. Yeah, and so I think it can just include, well, I suppose it's like what? It's like workspace folder slash vendor slash unity slash src, and that'll allow the extension to know that unity is a thing. I think so. Well, it's still loading. The extension is really slow. That's okay. So what we are going to do is we call the two functions, so void setup, and then void tear down. So we're gonna tear it down. And then inside of main, we can do, what can we do? Inside of main, we do what the guide told us to do, which was this. So we, instead of running all of this, we run that. And I imagine that this guy should live in the setup since it runs before every test. So setup here should be setting up the heap and everything. And then, ooh, what? Okay, run test, and then maybe we can call it, test malloc. Wait, did it have the name of the function or just, yeah, test malloc? Yes, that's perfect. But now it says that, oh, so a test should return this void. Okay, question mark? Sure. So we just do void and then nothing. So there should be no return, no nothing. And then that guy should be at peace. Yo, okay. So everything seems to be working. Let's do test malloc and then, right. So test malloc and then we return unity end. I'm going to delete all of these other cases, all of these other tests, just because we're gonna have to write something different for them and so on. And we still have the copy, so we can come back to it to take a look at what it was written there. Okay, so it seems like we have things set up, and I'm just going to see if autocomplete has it. Yes, let's go. Test, assert, test, assert. I don't know. Can I say, whoa, there's a lot of them. So how do I assert true? Yeah, test, assert, true. Is it true that true is true? Right? And so now let's try and make. So make test. And then we run test. Yo! Let's go! Whee! Wait, that's perfect. Okay, it seems like it works. I think it works. I think we're good to go. Let's go. Are you using default VS Code with only the C extension? Yes, basically. At least when it comes to development with C and C++, yes. The usual Microsoft C extension is what I'm using. Sorry, my desk here is a little bit fighting for its life. Sorry. Okay. I think we're good. We're good to go. Perfect. So. Now that we have this stuff, I think we also don't need this. Now we want to create our actual testing, right? So one of the things I think we may want is just something like expect block, which is the function I was talking about, where you pass to me a pointer to a given block in memory that you expect. You tell me what size you expect, and then you tell me whether or not you know this block to be free. And so the only thing we do is we do test assert, yeah, test assert. So we're going to assert what? We're going to assert first that going to assert that the size of that pointer is correct. And so I think we need to access the heap pointer for this. So we need to access the block that this is referencing. And the way we do that is we say pointer minus the mem heap low gives us an offset of where you are minus the size of IUINT 32T. And then we need to convert this into a UINT PTRT. And the same thing for you. Perfect. So now we know what the block is, and then we need to assert that the size of the block, right, is equal to size. So notice that this means that we have to test the BK asterisk functions, because currently we're relying on the fact that that is the case, right? That like these BK size functions actually work and they're actually valid. So you're going to assert that the size of the block is indeed what you want. And we're also going to assert, test assert, we're going to assert that, I imagine like it's better to use test assert equal or something like that. Yeah, equal. And then just include these two parameters. Perfect. And then we're also going to assert test assert equal, I suppose, equal bool. Oh, okay, equal. And then the block is free of this block to be whatever you expected, right? Great. Okay. So now that we have this, we can maybe take a look at something like, right, so I'm gonna delete this test, right? Every test needs to initialize memories from scratch. And then here, what we're going to do is think very deeply and, you know, hope that we actually do the right thing. So here we're trying to, let's try something simple. Let's do Nalloc and then 24 is a by line, so maybe 23, right? So if I try to allocate a block of size 23, then it's going to modify its size to be 28, right? Because it needs it to be 8 byte aligned. And so I would say something like, expect the block at A1 of size 28 and that it's currently not free. And that's going to be our entire test. So just to see if everything's working. So let's run make, and then we do test. Yay. Okay. I think that's good, right? Test malloc pass. Perfect. Okay. So let's try and see what happens. Okay, so my only situation, like the only sort of like thing that annoys me is that I would want to not have to calculate what the 8-byte aligned version of this thing is, because it the function internally changes the size that the user provides just so that everything is 8-byte aligned. And so if I do expect block to be of size 23, then this thing is going to tell me, no, the block is not of size 23, right? Which is a little bit, concerning. So yeah. How would we do that? Maybe we introduce, I don't want to say this, but maybe we introduce some sort of macro that like converts the size to what it's actually supposed to be. I'm not sure. So Hmm. 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 Yeah, how do we test it? So let's just for now, and I'm gonna change this later. I know. Everybody says that. I'm gonna change this later, but then they end up, using the actual thing. I think I'm going to just create a macro, right? And I'm gonna say align the size of a unit 32t plus whatever x is, and then subtract from the size of a unit 32t, and then we close all of this in parentheses as suggested in a previous session. And then now we can say, well, nalloc s23, or even better, we can create something like, 32 size 1, which should be like size of 23. Maybe we can do something like this. Yeah, maybe. And then I just say nalloc is 1, and then expected block of size is 1. Yeah, right. And so another way in which I think we could do stuff, which I think it's very decent, would be something like expect heap, right? And so to expect heap, we pass an array of blocks where a block is simply a struct that looks something like this. That looks like size and then whether or not it's free, right? And then we pass in an array of blocks, say an array of blocks of 2, right? And then, wait, 32 size, then bool free, something like this, right? It's just a proof of concept, so don't worry about it being yeah. So we say expect heap, and then we pass in an array of these guys. So we say like, oh, expect the heap to contain the first block to be of size this, and to be of size 12 and to be not free, and then the next block to be of size 23 and to be occupied. And then we can like test the shape of the heap as we go. I feel that's like a little bit more pretty, if you will. Yeah. So I don't know. Let's see. CT first. You say, have you ever tried GraphViz? No, I have no idea what that is. Someone recommended it to me last time and I want to try it. It's a graph visualization library for a project. Ooh, unfortunately, no, I haven't. Maybe somebody else in the chat has. Maybe somebody can chip in and contribute. But yeah, I unfortunately no. I have no idea. But yeah. So here when we're doing the struct, I think I just want to do it this way. Block. And then we can have some sort of function here that is void expect heap. Something like that, where we just pass in an array of blocks. So we need to, put this here. We pass in an array of blocks. We don't know how much there is, and then we need to pass in the size of those blocks, or like n, the amount of blocks. And then the only thing we do is for int I equals 0, actually for unit32t, I equals 0, that guy being smaller than n, and then I plus plus, we simply expect a block at that position. Well, it's not going to be as simple as that, right? Yeah, no. So we're going to say something like what? So, yeah, what do we do? What do we do? Shoopity-doo. 132T. Then I say something like current block. Right. Current block. And then I can just do, maybe we start our block to 0 or something like that, that offset. And then we say, okay, expect the test assert equal. Expect the block at offset current block to be of size whatever blocks in this position specifies for that guy. And then we do the same where we test assert equal. But this time, sorry, BK size. BK size, BK size. There we go. Current block and then blocks.size. And then here block is free and current block, right? And then block size. Not dot size, but instead dot free. Right? And then after that we say, well, now jump forward by your sort of size. Or I can just make it be something like, you know, it's equal to the next block of current block. Yeah, so then we test it that way. Now the problem is figuring out what this should be, because I don't think we have access to the red black tree. We need to find a way to find like, because currently what we have here is we have a static variable. Well, yeah, that represents the red black tree, right? And so the problem with that is going to be that in our heap, the first block is a block that's dedicated to internal use. So the heap, from the perspective of a user, actually starts like a few bytes after that. I think we can just say something like, you know, I'm just gonna hard code the size of the ghost node. Everything starts after ghost node. Ghost node, node. Okay, perfect. And that would be something like size of the block header, I think. Block header plus the size of the block footer. And then all of that aligned. I think that's the place where the current block start, where the ghost node starts. Yeah. So here, not accounting for padding. You'll see what I mean by that. Perfect. And so if we run this, we should be able to write stuff like this. Right? So right now, what I would write would be something like expect the heap to look something like the following. So a block array that only has one, and that looks something like S1, well, yeah, S1, and the whether or not it's free, that's false. Then we say there's only one block. And that should be it. Right? Yeah, I think so. Wait, let me read the chat. Yo, okay. Da-da-da. Why did you choose a red-black tree? The reason is because we're using a binary search tree to store our free blocks. And so that way we can look for the block with best fit sort of fast, right? Because, you know, it eventually becomes a search problem, and when you have a search problem, you know, binary tree. It's the first thing to think of. And in this case, it applies very well. There are two alternatives, at least they were at the beginning. It was, despite having a binary search tree, often you have the problem that like it becomes a stake or is not as efficient. So then you have self-balancing trees. And out of the self-balancing trees, the two sort of options that we landed on were AVL trees or red-black trees. The thing is, AVL trees require you to store the height of a given subtree, which is 4 bytes, while red-black trees only require you to store 1 bit, which is a bit of the color. So it was 1 bit versus 4 bytes. And so we decided that for better memory usage, we were going to use the red-black tree. Yeah, so that's the reason. Matt D, welcome. Oh, you're doing a mark slash sweep GC. I assume you still have pages within your RB tree. Are you using it for like searching through the free blocks when allocating? Yeah, exactly. Yeah. Not sure what you mean by sweep. Well, no, we're not doing a garbage collector. It's just like, like an actual memory allocator. No need to do any garbage collection. So yeah. And currently we're testing it actually. We're trying to test whether or not things. There's a few other approaches too. So putting similar sized allocation in the same pages that simplifies the search problem. Yeah. Like we had sort of a discussion on what the policies would be, right? We had it here in the Excalibur. Should we do best fit? Should we do first fit? Should we put them in different? Because I mean, there's the other problem where you have, you classify the sizes on categories and you put the blocks in each list for each size category, and so on and so on and so on. But we ended up deciding, oh, we're just gonna do best fit, right? Best overall fit over all the free blocks. And for that, using a binary search tree seemed reasonable because it didn't really incur much of a memory overhead. And on top of that, we got the login sort of search, which is great. So yeah, that's why. The benefit of that is that it's much nicer for multi-threading POV. Yeah. So currently, but currently we're just taking a look at this one, and we're trying to test it because it seems like it works. Wait, see, I feel like very weird because like although I see that it's compiling and stuff, I'm like I have the constant fear that it's actually not executing anything, and it actually like none of these things are happening. Um, yeah, unfortunate. Mm, let's see. The benefit of that is that it's much nicer for multi-threading POV. Oh yeah, we read that already. Um, uh, Zumba Kodo, thank you for following. As you don't need to lock the entire red black tree when allocating. Well, I okay. I suppose you would have to lock the entire red black tree. I was going to say, well, you just do hand over hand locking, and then you don't need to lock the entire thing as you insert. But never mind, because you would need to perform all of the rotations and stuff. So, but yeah. What do you mean by page? I only know nodes in a tree. You mean memory pages? Yeah. Oh, one last thing. Do you have any tooling that can look at cache line thrashing? No, not yet. Not yet. Nothing like that. Because we're currently doing this as like a learning project, so I'm not very experienced or something like that. We'll look into it. Yeah, let's see. So it seems like the tests pass, right? What happens if I just change this to a true? Will it just fail it? Hopefully, because if not, then okay, fail. Yay, perfect. Because this is gonna be false, and I think this is perfect for our thing. As I remember a paper from a while back that recommended sorting the start byte of memory pages so that all of the allocated blocks don't land on the same cache line. Interesting. Yeah, I haven't read that paper. Maybe we can take a look at it after we have like a working version of our memory allocator. Because I think this is a pretty good approach, I would say. I mean approaches and like further testing, because now that we have all of this infrastructure, we can just run it, right? S2 is equal to size of what? 53, right? And then we say, well, chance star A2 is equal to nalloc of S2. And then when we nalloc S2, we can say expect the heap to be first S1, which is allocated, and then S2 to be also not allocated. Okay, and then if I make this, oh wait, that's a 2. And that's also a 2. Yeah, okay, perfect. Make test. And then I run this. Yay! So one thing that I also think we could do is we could play around with blocks. Okay, I may be getting too greedy with this approach, but hear me out. Hear me out. Data, right? So what if we just play with the blocks the way we would in a memory allocator? So size, then free, then data, right? And then I assume data, well, it's the, it's the highest one, so then we put it at the bottom. Then something we can do is something like, okay, am I being too crazy for this? What if we create a function that's called create block, right? Well, create block already exists. So, something like create. And then when we do create, we can just pass in a block. Actually, no, that makes absolutely no sense. Because we can just create the block struct. And then when we create the block struct, actually, never mind. I think, wait, yeah, I'm getting a little confused. We can create some sort of block, and we can pass to it the size, and then pass to it like the data. Right, so char star data. And then what we can do is we can call it something like this. We can return a block, right? Block. A block struct that just has size, then false, then data. So something like this. And then we can take, well, this as a given string. Just hear me out for a second. Hear me out. I know. I know I'm not explaining anything, but block is equal to block. And then we can make this little window and have size be size, free be false, and data be some sort of, null pointer. But then we say block.data is equal to nalloc whatever the size is, and then copy into it the things from the string. So stir copy into block.data all of the string information and whatever the size of the string is, and size, so un32t info size, then we include info size, and then we return whatever this block guy is. Something like this. Wait, how does string copy? Oh, of course. Yeah. Sorry about that. So then we don't need the the size of the information. Perfect. There you go. Okay. Type name not allowed. I think I can just do it this way. Yeah, perfect. Let's see. Whoa, there's been a lot of messages. Whoa. Okay. Memory pages. As I remember a paper from a while back that recommended sorting. Yeah, we read this. I think there was something, read this lab allocator paper which was used in Linux. Interesting. We can read that actually. But I've been in C# for a long time, so I've not had to worry about memory for a bit. We always did largest order descending for structure layouts, although it probably doesn't matter. Yeah. It's a stir copy. Isn't that vulnerable to buffer overflow? And then such a question. Why not just allocate the entire struct and do a complete memory copy for the entire thing instead of piecemeal it? I mean, wait, why not just allocate the entire struct and do a complete memory copy for the entire thing instead of piecemeal it? You mean the block struct? I mean, it could be either way, right? But I kind of don't really. It doesn't really matter, right? Because then we can just do this instead. Then we can just copy whatever data they give us. And so the way I want to use this is to be able to write a test and simply say something like this. Simply say, like, block 1 is a block that I want to have size 23. And I wanted to have the following information, right? Like, hello, everybody. And then block 2 is of size 53. Block B2 is just of size 53. And I wanted to have the information bye-bye, right? And then here in the heap, I just need to specify, like, oh, expect it to be something like B1, right? Block 1, and then block 2, and then, right? Expect the heap to look like block 1, block 2, and that's it, right? So that's like kind of how I want it to look, so that it's very simple, and we can just specify the blocks. We can specify in which way they should be arranged, and that's it. So that's what I mean. Let's see. Even though that's wait. Struct memory instead. Oh, you have a char star. I would not use stir copy. Even though that's char star data, what you're really saying is it's a block of 8-bit values. You wave it off using memcopy and safer version. So what do you mean? You're really saying is it's a block of 8-bit values. You're way better off using memcopy. What do you mean? Like, yes, but like I'm using the char star just to pass in a string. Like it's supposed to be a string. I just don't want the function to be like create and then hello everybody and then like, oh, how many characters does this have? And then have to say 15. And then when I update the string, have to say, oh wait, how many characters does this have? It has 21. So then 21. And so on. I just want to be able to just write a string and then don't worry about it. This is not going to be, critical code or anything like that. This is just for the tests, and it's not going to accept any sort of external input. It's just going to be us. So I think it's acceptable to just have this for the ease of writing the test. So yeah, I assume just thought data is intended to be the size of your allocation. Yeah. So I just want to put in like a string and be like, yeah, just put something in there. So yeah, and so that way we can create the blocks like this. And then I guess one good thing would be, yeah, I think if we simply sort of abstract away the fact that we need to pass in some data, right? We sort of automatically create data that we keep track of. We try and see like, okay, you know, so what I'm thinking of is we fill in the entire block with random values, but we try to use all of the space we have for the sake of allocation. And then once that's done, every single time we verify that data is still there. So something like, okay, it's starting to look a little bad, but bear with me. If we create something like, you know, random string, like random.str, and then we just pass in a size of what we want that random string to have, size. And then we like generate some random string. Then we return that. For now, I'm gonna return null. And then what we can do here is when we create a block of a given size, what we're going to do is we're going to say, well, right, we want this guy to store the information that's present inside of that random string, and we just keep track. So what I'm imagining is something like this, right? Create a random string of the size of the entire allocation, write it into the allocated block, and then keep track of it, sort of like block pointer, or like pointer, and then store here sort of like expected data, right? And then we pass to the expected data whatever the data is that we want to store. And so every single time we're able to check whether or not that block still has that data, to see that we haven't overwritten anything. So that is like the ideal situation, in my opinion. Since we are gonna write this function, we're gonna just make sure that it doesn't overflow or something like that. It's always gonna have the size, and it's just a string. We don't intend it to be something, you know, that's gonna be in production, so it's gonna be fine. And then here, when we call this, we want to test not only that the size is correct and that the free is correct, but we also want to assert that equal, maybe they have string. Yeah, okay, string. Expect equal string to be whatever my block has. So the block's information, which we access by doing a little bit of a trick. We do by grabbing the heap low, right? We convert it to a chance still. So you grab the lowest byte of the heap, then we add the block offset for the current block we're in, and then we skip the header. And that's going to be the pointer to the actual block. And then we're going to simply verify whether or not there's something over it, right? Which should be the little guy over here. What's his name? Yeah, block set I, the ith position dot expected data. And we also need a size of the string. So if the data ever gets corrupted, right, it's possible that this no longer has a null terminator. So, well, I assume that test assert equals string is able to, because we know this one is well formed. So it's going to be able to stop eventually, given that this one is well formed, and then it's going to reach an null terminator, and then it's going to say like, oh, okay, never mind. So I think this is fine. And then, yeah, perfect. So B1, B2, and then we, yeah, awesome. Let me read the chat. Read the chat. So, but safety, think of the children. All right, buddy. The way we used to do that as you're doing Realloc was to send the entire buffer with a particular value, or this, and then subsequent Realloc over it replaces it with BBBB at all. it's easy to test whether the realloc actually override. Yeah, that's exactly what we're doing. Yeah, there's nothing different to that from what we're doing, because it will be the correct idea, right? So I just want to write random values, because if I write something like, because we don't know what the user wants to do, the user being us, right? We don't know what we want to do with that block. Maybe we're testing a free, maybe we're testing a malloc. So creating a random value and keeping track of what the value is better. If it was like a, and then like all the time, if we do a realloc, then we don't know whether it was replaced or not. So I just creating random values, and then that way it's like easier to test and see that everything is actually in place. Also means you can look at the page in the memory debugger and see exactly what's going on. Yeah. So something similar. It's just that the idea is that realloc would always give it an incremented value. What do you mean on an incremented value? Like, for as this is your test, your code. So, in the case of Realloc, I can see it, but so I guess, let me think. I guess there's something that we could do just to make it simpler to read. We could just keep a counter on. Sorry, guys. Give me a second. Okay. We can just keep some sort of global counter. So what I mean by that is how many values can a, can a single byte have in hex? Well, 128, right? Well, 255, sorry. 255. And so we can just limit everything to be at most 255 blocks. That is, during tests, you can create at most 255 blocks. Then as we increase that counter, every new block just gets a new identifier. So what I'm saying right here is something like this. It's something like uint32t, and then something like block ID, right? Then it starts at 0. Then every time we call generate random string, what we do is we increase block ID by a given amount. We increase block ID by after that. And then when we generate the random string, we simply do whatever the hex code of like yeah, I think that's the case, right? I can just do something like str is just char string, and then I say size, and it's we just keep it there, and then for int I equals 0, I smaller than size, then plus I, and then we just do string at I is equal to whatever the block ID is. And then we populate the entire thing with that. Then we return that string. It's gonna be in the stacks, of course, not correct, but I'm just gonna use malloc for it, like the actual malloc, because once again, this is just for the sake of testing. So let's not worry about it. We have malloc and then the size, and that's it, right? Yeah, I think this is the way we want it to be. And then the random string is just gonna be a b b b b b b b c z z z d d d d d d d d d e e e e e, right, and so on. So yeah, I think it's a great suggestion, Matt. Definitely makes it easier to read. The main issue you run into with random test values, and you should use random test values too, is that when you or a human tries to debug what the hell happened, it's much harder to see what went wrong. Yeah, no, that makes total sense. That just made total sense. You should test totally random data too. Yeah, of course. But for now, I think like this, this is going to be good while we sort of, create the testing infrastructure from the ground up. We're just gonna have predictable values and stuff, so that it looks better, and then then we're going to create the random data. And we just have to replace this function and then run everything again. So either way, I think it's going to be fine. And I think this works, right? So every time you create a block, you end up increasing the counter, which makes the identifiers be different, but all of them are continuous and the same. Um, and then we expect the heap to look a certain way, and then that certain way we already know what it looks like, and thus, it's easy to verify. So let's try and see if this works. Sorry, not test. I need to recompile. Let's recompile. Hello, where are you? Oh, did I just get rid of? Oh wait, no, never mind. We have a make file. Yeah, make test. Make test. Perfect. Then we do /test. Yay, it passed. Okay, so it seems like it verifies very well everything. So what happens if I just make b2 dot expected data to just be some random thing, koala, right? So we should see this thing complain. We make, we run. Yay! Okay, let's go. Oh, dangerous. I imagine we don't start at 0. We want to start at 1 because these are strings. So, anyways, perfect. Okay, that sounds awesome. So we have laid down the foundations, and now it's really easy to test because then we just say like, oh yeah, I want to create these. I want to create 3 blocks, right? Then the third one we have with size, I don't know, 12, right? And then we want to free the block, the second block. We want to free B2. And so we expect the heap to look like B1. I guess if we can implement the functions, like block free and like block free or something like that, then it's gonna be better. And then yeah, I think that's nice. Let's see. Also, don't forget to test things like allocating a block of memory, for example, 4K bytes, that make you struct out of that 4K block. For example, the first X bytes are your struct, and you set the chance style pointer to the next byte of the 4K chunk after the struct, and then fill that. Whoa, let me read that again. Don't forget to test things like allocating a block of memory, for example, 4K bytes. Make your struct out of that 4K block, for example, the first X bytes are your struct, and you set the char star pointer to the next byte of the 4K chunk after the struct, and then fill that. So you mean that to be like the user is overwriting memory that they shouldn't overwrite? Is that what you mean? I'm not sure what you mean. Let me know, so that I can know exactly what you say. But yeah. Meantime, I think yeah, this is exactly what we want. And so now, by the way, how do you align the pointers you return to the user? So that is the thing, right? Like we perform a bunch of alignment. That's why you see this as macro here that I had to include, because like if you create a block of size 23, the memory allocator is gonna actually not give you a block of size 23, it's gonna give you a block of size 28. And so if you try and say, like check that now the size of block 1 is 23, it's gonna fail because the memory allocator actually aligned it to size 28. So this S guy just aligns the sizes in the same way the allocator does, so that like we can have, we can match the behavior. The way we align things is just very simple. Whenever the user, yeah, no, don't worry. Whenever the user here, right? So whenever we initialize things, whatever the starting the starting byte of the heap is, we introduce padding to it, right? So we try and align the first byte of the heap, and then we subtract on it, right? So we try to add padding so that the beginning of the heap starts at an 8-byte aligned address. And then after that, we introduce the ghost node, which is just internal structure. So just remember, from now on, the heap starts at an 8-byte aligned address. And then we just ensure that every block is 8-byte aligned. Or like its space it occupies is a multiple of 8. So the size of the header is, if the block it's allocated, it's like 4 bytes. And thus we align the size that the user gives us to the next multiple of 4, such that that plus 4 is 8-byte aligned. So for example, as I said before, if you give me the size 23, I'm going to align it to 28. I'm going to make the size 28. Now 28 is not a multiple of 8. Right? That's because this is just the size. And that 28 plus the header, which is 4 bytes, gives you 32. And so now you're 8-byte aligned. So you just ensure that the heap starts with an 8-byte aligned address, and then you make it so that everything is 8-byte aligned as you go through. In the meantime, we have not followed this specification when like the pointer you provide to the user is 8-byte aligned. We have the pointer that is provided to the user to be 4-byte aligned. We can easily change that by just changing the size of the header to 8 bytes. But yeah, that's all. We used to use the whole grab a block of memory, stamp it with data which was a struct, and then fix any pointers up to point to the correct offset within the block. Grab a block of memory, yes. Stamp it with data, so then we fill it, right? You just call that data we filled with, called the struct, and then fix any pointers up to point to the correct offset within the block. I'm so sorry. Wait, I still don't know what you mean. Fix any pointers up to point to the fix any pointers up to point to the is there a comma there? Wait, and then fix any pointers up to point to the correct offset within the block. So what do you mean to fix to point to the correct offset within the block? You mean it like the struct? But then your struct does it automatically, no? If you just access the member variable? Wait, AMD64 uses 16-byte alignment because the user might want to store or something like that. Yeah. Like it's something that we can take a look at. For now, once again, this is a very naive implementation initially because like we're just trying to learn how to create an array allocator. We'll concern ourselves with like all of these other details that are easier to implement once we actually have something that works. But yeah. So for now, I think this is it. I think we can. So we have this create function. I'm just gonna call them, bnalloc, like block nalloc, and then I'm gonna call block free. And you give me the block that you want to free, block B. Then the only thing we do is we call free on that block. So we call mmfree.b.ptr, and then we return. And I think we're gonna be fine. So for example, the way things work here would be self-create equals block nalloc, and then we call something like, block free, and then free block 2. And then what I expect is to b dot free equal to true. So something like this. Although, see, I don't like this interface because yeah, because it's like I don't like how this looks because then the entire test is like obscure to me what I expect at the end, right? Suppose that I introduce like thousands of lines and then all I see is expect heap B1, B2, B3, right? Like, am I expecting B1 to be free? Am I expecting it to be allocated? Am I expecting a certain size? What am I expecting? Um, yeah, so I think we're just gonna have I think I just prefer the approach. What do I prefer? Because okay, I think that everything is just in the way we write this expect. Because then I can just say expect the heap to look something like, so we're storing the size, the free, the pointer, the expected data, right? The size, the free, the pointer, the expected data. So the size, I'd say, well, I expect it to be a b1.size. And the free, I expect it to not be full, to be false. The pointer is just gonna be there, right? I might. Okay, give me guys a second. I'll be back in like 1 minute. Hello. Hello. I'm back. Okay. So I just want to get some frosted flakes. Because I just wanna eat something because it's a little frustrating. Because I want to discover like a good interface that allows us to test everything in like a good way. What do we do? So I want to be able to say like, you know, expect this size, expect it to not be allocated or to be allocated, to not be free, and also expect this data. I want to be able to specify those three things and just let everything flow. So yeah. Um Let me think. If we run B1, let me do. Wait, there are messages in chat. Okay, need to bounce, but go look up slab/sloob. It seems it's a mono variant or arena-based allocators. Good luck, and don't forget where your V table went. Yeah, of course. I'll take a look at it, but I don't want to look at it now. I don't want to bias myself with anything because we designed this from scratch. Sort of every decision was our own, and I want to make the memory allocator a result of like the stream, and then after we're done with it, then we are like, okay, how can this be improved? If we want to stay with the memory allocator, if we want to migrate to a different project, then we can just do that. But thank you. Matt D, thank you. Very, very good advice. And yeah, we'll be trying to find a way to design this. So I think I don't know. I don't know what to do. And I guess we cannot really test size. So what I'm thinking of is Realloc, right? There is no way to specify and say, this is the size I expect. Because Realloc, if you say Realloc 65, it may give you a, you know, a block that is indeed of size 65, or maybe a block that is of size 68 for a by alignment. Or maybe the only block that was free was one that had size 72. So then it gives you 72 because it is not worthy to partition. So you don't know the size of the blocks that you're going to get. So we cannot really test for size. So the only thing we can test for is the data that we're storing inside them and whether or not they're free, right? because size is unpredictable. So I think, and that's what was bugging me out. Like, we cannot store size, right? Can we store whether or not the block is free? And the answer is yes. Can we store the expected data? Yes. And after that, nothing else. Right? So, yeah. Yeah, I think so. So if we don't test for size, if we don't test for anything, then what do we test for? We also need to assert that when we reach the last one, it's actually the last one. Okay. So, yeah, this is a little annoying. Yeah, so I guess we can just, we have to limit ourselves, since there's so many things that we don't know, to just do like, A1 is equal to like Nalog. Then we Nalog like however much, 23. Then we copy a given string into A1. Then we keep track of it and then we say, okay, right, like, this guy needs to be free and then needs to have this much data. Yeah. Okay. I guess that's the way of the water. We just do string. We just do a random string. I just want to obtain a random string of size maybe 23 or 24. And then all I'm going to do is when we now look A1, we just copy into A1 data 1. And then here we just have to verify, well, does this contain that string? Right? And then that's it. Because it's literally the only thing we can measure together with whether or not that block is free. So yeah, I think that's all we can do. So now we run make. Oh. Well. Oh yeah, I think we're not going to use this anymore. If we run make, and then we... Oh. Okay. And then we run this. Should be able to pass? Ooh. But it said was no. Okay, what happened? What happened? What happened? So character D1 What? Blocks I dot expected data. Yeah, no. Wait, what does block contain now? Oh, it contains a pointer. Yeah, no. We only needed to have this much. Be free is not a thing anymore. And then there's another error. Where? Okay, perfect. I think that we're just gonna keep it, simple, because there's not much we can control. So what we can do is we can do this, and then notice that it passes now. And then, so maybe I just create like, even better. We can create something like this where we do, a chart star array called data. And then for data, we just allocate, say we're going to create, I don't know, 10 blocks, right? And then what we do is we say, well, print I equals 0, I is smaller than 10, and then plus I. We just populate it with a bunch of random strings that follow the convention that we established. And then we just, I don't know, we make it like every single block be 40 bytes long. It's got to be a little more than 40. It's going to be 44, but you get the idea, right? And so then after we generate it, we're going to say, well, choice array 1, right? It's going to be maybe one of those blocks. So maybe I could generate an array that's called blocks. And it's also going to be 10 blocks because, right, each block corresponds to one data. And so all we do is simply say something like this: I is smaller than 10, and then plus I. And then we say, well, blocks in the ith position will be equal to allocating 44 bytes, and then copying the information from that string into, actually it's 43 because the null terminator also counts. And then we string copy into blocks I the data that's stored in data I. Perfect. And that way we have like, 10 blocks, each of which has data, and then we can just play around with them. We can say something like expect the heap, right, to have 10 blocks, each of which is going to look like this, right? All of them are allocated, so true, and they're gonna have, in this case, data 1, data 0, and then 5, 6, 7, 8, 9, 10. Okay. And all of them are allocated, and then they're gonna have that information. 4, 5, 6, 7, 8, 9. And then we just, comas everywhere. Let's wait. Perfect. And that should be like, oh, we expect the heap to look like that. And then if I say something like free, and then I try to free the second block, blocks 1, then I expect the heap to look a little bit different. I expect it to look something like this, where I have the same heap, but now this guy is gone. So it should be false because it's, oh, sorry, this true. Well, I guess I prefer to indicate that it's allocated. Yeah. Okay. Then expect heap. Perfect. And then after this, we say that this assertion should only run if the block is allocated. If it's not, then ignore whatever data they give us. Right, so something like this. If we run this test, it should pass. Great. So now we're able to control the heap in that way. So I'll give an example. I'll give an example with Realloc. With Realloc, and then this is gonna be the 3 blocks problem. So the 3 blocks problem. Stephen Blumvan, welcome to the stream. Wait, Stephen LB, yo, welcome back to chat, yo. Today we're testing stuff. We're creating like our testing infrastructure to, or like the API for tests, if you will, to know how we're going to test everything here. Yo, wait, that's perfect. And if you share with your team, I'm glad. But yeah, here we're eating frosted flakes too. Sorry if I sound a little depressed. It's just that like tests are like so annoying. They're like one of the worst things in a program. I don't like tests, but there's no crime. Oh, Penguin Operator, welcome back. What are you creating? Oh, we're creating a memory allocator. We're creating a memory allocator from scratch. Yeah, we already implemented malloc. We implemented free also, and we implemented Realloc. And so now we're trying to test everything in a more like automatic way. I don't know how to, what are you creating? Valley 2454, welcome. Sounds like some sounds like someone who does too much unit testing would say. No, 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 that's not something someone who yeah. Then like someone who does too much unit testing with it. Like yeah. Unit tests are just absolutely insane. It's been you're in USA? Oh, yeah, I'm currently in the United States. Oh. Accept our Lord and Savior fuzz testing into your heart. See, like the thing is, I haven't ever used a fuzz a fuzz tester before, and like we have the problem that like although it has to like it's just that I don't know it enough to like know how to use it, and probably it would imply that I would need to like learn about the fuzz tester and stuff, which I will do in in like out of stream time. But I don't want to bore you guys being here like, oh, let's see, how do we set up the fuzz tester, right? Because I imagine it's like you need to do it with like a bunch of other stuff. You need to connect things together and stuff. There's also the fact that like the fuzz tester, like from what I understand, it just flips bits around to see if like you manage everything correctly. But we need to preserve some things in our blocks. I think Stricknit said that we can fuzz test with some structure, but it seems to me that that's basically kind of what we're doing. Like, of course, we're not running a fuzz tester, but what we're doing is just like creating scenarios and then putting random data in the blocks and then adding expects to show what we expect the heap to look at after some amount of time. So yeah, like I'm not sure how we could do something like it. or how we could implement it into here. But yeah, when you download messages, snapshot testing is pretty good too. Go on. And Stephen Blumfan says, "How many program language do you know?" Not that many. I know C++ is the one I mainly use. Then we're currently coding in C. I'm not sure if I'm good enough to say like I know C. I know as much as a C++ person knows about C. And I know some Python, and then like the web technologies, right? Like TypeScript, JavaScript, and stuff. And that's kind of about it. That's basically it. That's the most I can give you. Like I don't know much else. Yeah. If I have to learn Rust or Go or C++, which one to pick? I don't know Rust. There's a problem. Like it's one of my goals to learn Rust here on the stream. That's probably the next project. Go I've used. I've used Go. And honestly, I do know people often recommend do not start with Rust, and I feel it is a good recommendation because everything is better when you understand the reason why it's there. And many of the things that Rust implements, despite me not having any experience with the language, like I know what the purpose of Rust is, and like I've heard of it, and like the barrel chicken and stuff. Most of the things that Rust introduces are there for a reason, and you understand the reason if you learn C++ before Rust, in the case of like C++ versus Rust. Go has a garbage collector, so you don't understand as much of the what happens with memory and etc. I also don't think it's necessary. It really depends on like how low level do you want to go. I would recommend C++ because I'm biased. I'm biased. I like C++. Go is also a good starting point, to be completely honest. I do know Rust is maybe not the correct point to start. Rust is like after you learn either C++ or Go. More like after you learn C++ and then have to face all this site faults and stuff. But yeah, fast testing works best with defensive programming because you don't need explicit expectations. You can just see if it trips. And I said, yeah, exactly. So, but in my case, like we need the blocks. Like we just expect data to be there and the blocks to be arranged in a certain way, which is what makes it like a little bit difficult to see how we would use a fuzzer. But let me know if you have an idea. I know Python, Go, and TypeScript. Yo, pretty good. That's a pretty good combo. Of course, some people use asserts for things which can all be to happen, which reduces the value of testing. I do think learning about lifetimes first from Rust, like I did, is a bad idea. Ooh. This month, my goal is to learn observability and E3 playwright testing. Damn. Well, but maybe not by that much. Okay. I see. But yeah. So, okay. I think I'll give you guys an example of like good things we can test. So an example would be this. So we can create an array of data, right? In which we're going to store a couple of things. So we're going to store give me a second. So we're going to have 3 blocks, each of size 40. Actually, size 44. So that is 4 less than an 8 by the line thingy. And, oh, sorry, these are the sizes, actually. So never mind. Instead, we're just going to create like data 3. Then we do 4 int I equals 0, and then I is smaller than 3. Then plus I. And then what we're going to do is we're going to say, well, the data at position I is just going to be some random string, which is not really that random, to which we're going to ask it to be 44 bytes long, 43 actually, because the null terminator is one more byte. And once we've done that, we are simply going to say, well, we're going to have 3 blocks. And for those 3 blocks, okay, and I is equal to 0, and then I is smaller than 3, then plus I. For those 3 blocks, what we're going to do is we're going to say, well, block I, it's going to be equal to what? Well, to an alloc of size 44, and to which we copy the data that we just generated. So I think it's better if we just put things this way. Did I? And then string copy to blocks I, data I. Perfect. Then we can eliminate this for loop. And so what we want to test is, well, we expect the heap to look something like this. So we're gonna have 3 blocks. We have 3 blocks. And then I'm gonna do this. There's 3 of them. We expect the first block to be allocated and to have whatever data 0 stores. That's why we created the data array separately, so that we can check that the information's still there. Then we expect it to be allocated here, and then data 1 be present. Then we expect it to be data 2 be present. And we also expect, right, test assert less than or equal to. We also expect the size of the heap to be less than what? Less than, these are 44 bytes, so 44 times 3 plus each of the headers being 4 bytes plus give or take, 20 bytes. So there's that many blocks. 44 is 3 times 4 bytes times 3. So what I'm saying is the heap must be of at most, each block, it's 44 bytes. Then the headers of each block. And then the 20 bytes from the ghost node, I suppose, right? Plus, let's say, give or take, like... Actually, no, this also doesn't work because we don't know how big the heap can be. Yeah, we don't know how big the heap can be. That's a little annoying. Because... it's like... wait, let me read it. Seems like you don't have development experience. You're good with DSA. Thank you. But yeah, I don't have much, like, experience with, like, a build system or something like that. I just, like, write programs. But yeah. And, like, I didn't know about Unity as a testing framework and stuff like that. So I'm a little inexperienced on that side. Don't eat junk food. Yeah, that's true. But, like, Frosted Flakes taste so good. They're, like, the only junk food I consume. Penguin operator as friendly as usual. If you factor out the constants into function parameters, you can use randomized testing on this, which will be less work and find more bugs. So can you describe like how, like what your idea is? Because I think like what I had in mind was, because before we had something similar, which I'm starting to regret we went back to it. We like, you know, we didn't do that. And as we had this block struct, let it let it rewind. Give it a few seconds. Well, we had this block struct that um there you go, there they are. So we had this block struct, right? And I'm actually gonna copy this file and I'm gonna paste it here, which is another copy. Copy two. And then I'm gonna rewind. Oh shoot, no! No! No, I wrote something down. Oh no. Okay, that's fine, that's fine, that's fine. Well, never mind then. We just went back into the fast. But basically what I had was oh sorry, I'm in test. Was we have this sort of naive implementation of sorts where we create this block struct that simply has the size that a block is supposed to have, whether or not it is free, and what data we expect from it, and then a pointer to like the actual block in memory. So what we would do is we would say, okay, generate some random string, right? We generate some random string and we populate the block with that. We created this bean alloc, which simply what it does is it creates some random string of the size that we want to allocate, creates a block stub that contains or keeps track of the information the block should have. So it should have this size. It should not be free. This is where it's going to live in memory, and it should have this data. And then we return. So notice that when we do nalloc here, we populate the actual block in memory with that string. And so what we do is we would end up saying something like this, right? Block 1 is this, block B2 is this, block B3 is this, then free block 2, and so on. And then we would expect the heap to be like, in this case, right? B1, B2, B3. So it's like we are running a toy memory allocator, like a memory allocator that just doesn't allocate anything in memory. And those are like these guys, right? And then we do all of the steps we need. And at the end, we compare the fact that both the toy example and the actual implementation match on the data that they should have. So that is what we've been doing, like we were doing before. But then I was like, this doesn't seem right. But the more I think about it, it seems like the correct approach. Maybe some of you guys can weigh in on what you think about this. But yeah. Let me read. Which would be less work and find more box, yeah. Nice. So you would be good at making optimized binaries. What does that mean? Wait. Oh, you mean like optimizing stuff? But I don't have much experience with that either. Like I'm not sure. So can you create a program to optimize image? As we pass a 1000 by 1000 pixel image and your program returns the desired size example. I mean, maybe I could. I'm not sure. I mean, it is a little bit of a strange hypothetical, but maybe. You know, if I really set my mind to it, maybe we could create such a program. Stephen Blumenthal, you say, so you do job or still studying? No, I'm still studying in college. I'm still studying in college. Yeah. Simbleed, maybe you should look into packed structs for memory alignment help in memory allocator. Oh yeah, no. We already have all of that. With the memory allocator alignment is not something I'm concerned about because it already aligns things. Is it that it aligns it to values that are not the usuals? Like currently it aligns it to 4-byte, for example. The pointer that it returns to you, it's 4-byte aligned. So that would be an example. I think that approach will seem better the more complex the actual allocator gets. I get that it might seem pointless when the toy isn't that much simpler than the real. Yeah, yeah. So I'm like, all right, buddy, like, what are we doing? But but yeah, so I think this approach may be a little better. It's also not that it's that the toy example is really close to the actual implementation, because notice that what we're doing is simply storing what information it should have, and when we free, we just set free to true, and then we actually free. So like this function makes the toy example like become whatever it needs to become, and then it calls the actual thing to do what it's supposed to do. Um, and it seems like the toy example is simple enough to the point that we could do this. Now, the problem comes with alignment. And what I mean with alignment, I mean that suppose, for example, that we have something like this, right? We have this block is allocated, this block is allocated, this block is allocated. Then we free block two. And then we do something like this, right? I want to allocate some other block, which we're going to call block four, that has size, let's see, size maybe 48, right? Size 48. Or size 52, which is the next alignment that it's going to take, right? So what happens here is there's only one free block, which is block 2. And it's able to accommodate something of size 52. And so the allocator is going to use this block of size 53 to accommodate this request of size 52. The thing is, we know that only if we take a look at this, right? So what I'm saying is, when we expect the heap to be of a certain size, this Alloc will expect the block to be of size 52. But the memory allocator is not going to give us a block of size 52. It's going to give us a block of size 53. Because for the memory allocator, partitioning the block of size 53 into something smaller to fit 52 doesn't really make much sense, right? Because it's only 1 byte of difference. So it's just going to say like, nah, right? Why would I partition this block? And it just gives us the entire block. And so measuring the block size, it's not plausible because we don't know like which block it is going to give us and what size that block has. Now, currently we do know. So we could opt to simply testing the allocator, knowing all of this stuff, knowing, oh, I know that the allocator is going to return this block and so on. The problem with that is if the allocation policy ever changes in the future, all of our tests get completely invalidated because the allocator selected a different blocks from the one we expected. And so now the size is different. And so now everything is ruined. That's like the thing that bugs me about the memory allocator, because if we decide to do things too close to the metal, then our tests end up testing like not the memory allocator in general feeling, but like a specific implementation. You're saying I don't think you should test that part then. Yeah, exactly. So now we're not able to test the size of a block, right? We're just able to know or to test what data the block contains. But then that's a little bit of a problem because like, how do we know whether the memory allocator is doing what it's supposed to, right? Like whenever, for example, whenever a block is freed and it has a free block by its side, the memory allocator is supposed to merge the two blocks. But if we cannot test for size, we cannot know if they really merged, because you would need to know the size, right? To know how big the new block is, to test that the block is actually there. You could still test that the block is big enough though. Yeah, I guess so. Like I have the fear that like maybe there is something that makes like a block humongous. So then it's like, oh, this block is supposed to have like, 2 bytes, and then it's like 50, and it's like, oh yeah, no, you passed the test because like, I don't know. Um, I guess actually, now that I think about it, I think you're right. I think you're right. Um, Valley, I think you're right. Because what we can do is we can maybe not test the exact size, but we do have an upper bound and a lower bound on it. So the lower bound would be the size we specified, and the upper bound would be that thing aligned to the next multiple of 8, or sorry, the next multiple, the next number that is modulo 4 with respect to 8 plus 20. That's an upper bound. And then we can test that the block size is between that range. And it's not that implementation dependent, right? Because if you're giving me a block that surpasses the upper bound, it means that you're wasting space by giving me this huge block for something that is relatively small. So I think we can test with the bounds. I think it may not be over. I think you're right. Yeah. It sounds like a better. Yeah, yeah. I think that is a better approach to create our testing like API or like. Yeah, that sounds very good. Let me read some messages here. Sorry, guys. I like I tried to do the explanations like or like the thought process, and then I don't read the chat in the meantime just to have like a continuous line of thought because then we get lost. Um, I can see one day you would write an OS better than Android. Thank you, Stephen Blufan. I'm not sure about that. Like writing an OS is like incredibly difficult. Um, I was seeing D Ferrari's stream yesterday. It was like working on his Windows system for his OS, and like I don't know. I don't know if like I would ever be able to like. It just feels like such a titanic task. Um, but who knows? Who knows where life is gonna take us? For the Linux kernel page, size 4K and TLB mostly 128, external frag is larger trade-off over internal. Most aligned for page size or at least cache line size. Um, yeah. Simply. So that is something that we should have into consideration. What I'm saying is we don't really need to worry about alignment because all of the sort of tooling or sort of things we need for that to happen are there. So whenever we want to implement the alignment, we just change some numbers and it's gonna work. For now, we have a very basic alignment, but we've been designing the memory allocator so that you can align it to to, to something you want. So yeah, don't worry about that part for now. SC page size does take on XMU kernel. Okay. Um, Maybe you could do snapshot testing of it, but maybe not even. Yeah, it would be difficult. Like at least. Yeah, so that was the thing. You could still test that the block is big enough, though. Yeah, and then that's the actual variant. I only know these TypeScript, JavaScript, Node.js, React, Next.js, MongoDB, Postgres. Whoa! Worker serverless functions. Whoa! AI interview simulator. AI resume builder. That's very suspicious. Okay. Web playground, real-time notifications. Brother, what is this? Okay. That sounds like a much better thing to test. Yeah, thank you, Ali. The important thing in testing is to think critically about your actual invariants. That is true. I guess like I haven't really ever created like a rigorous set of tests. Um, Mostly, sometimes you're provided tests and then you just use them. But now that I'm like creating actual tests and I really want to think about it well enough to learn, um, it starts to show like why it's so important. Rather than just freeze implementation details. Yeah. Crazy moment to join the stream. Differ, yo. I mean, I have build web ideas, which opens. Yeah, I imagine like the web is very popular. Um, Personally, from years of experience in Linux kernel upstream, I can definitely save you building Hobby OS, make a bootloader, basic MMU, and scheduler, and then start going deep in one system. Personally, I went deep in kernel data path and network subsystems. You learn a lot. Wait, that's a pretty good roadmap. Interesting. We'll see. That could be one of the things we end up doing in the future for a project. Um, I meant I have built AI interview. Oh, you've built those. Oh, damn! Wow, that's a lot. There's specific tech. Yeah. Okay, perfect. So welcome everyone, and let's continue with this. So we're gonna have the toy allocator perform all the stuff that it needs to do as well, and then like run in parallel with the actual allocator. And then they're gonna be like, at the end we compare the two. And since the toy example is so simple, it should be the same as this guy. So I think that's a better testing sort of idea, like mindset of what things should be. Um, yeah. So one thing that we have to have in mind is yeah. So we allocate, then we be free. And we said that when we're doing the expect heap, we want to compare sizes, but like in a different way. So what we want to test is size. So we want to test assert that this thing is less than or no, greater than or equal to um you know the okay, so assert greater than or equal. So which one goes first? Threshold and then the actual. Okay, greater than or equal. So it would be something like blocks I dot OG size. Like, I don't know how else to call it, but the original size of the request. And then our block needs to be greater or equal to that, right? So now let me, struct name has no field OG size. Oh yeah, of course. So here instead of size, we're gonna just do OG size. Because it's not the size of the block, it's like the size that was specified at the beginning. This we don't need anymore. And so we test that it's greater or equal, and then we test that it's smaller than whatever the lower bound is. So less than or equal, then we test that blocks at I dot OG size. So the OG size aligned to 8 bytes plus whatever amount you need to have as a threshold in terms of size. So this is an important number. I'm going to define it here at the top, right? I'm going to define something like I don't know, partition threshold. So one thing that we need to do formalize better the partition threshold. Actually, I think we can just do that right now. We can just define the partition threshold inside mm.h, right? Yeah. I don't see why not. And then what we can do is this partition threshold, it's gonna be something like 16, I think is the current value. And here where we go to partition the block if it's worth it. Let me find it. Where is it? Hello, where are you? Where are you? Partition block, there you go. I'm gonna assert that this is greater than or equals to 16. Where is partition worth it? There you go. This plus the partition threshold for like a size or like space in total. And so it's gonna be 20 actually, yeah. Okay. So we partition, our partition threshold is like if the block is and the difference between the block space and what's actually being allocated is greater than or equal to 20, then it is worth of partitioning. And so that's what we're just going to use here in our test. We're just going to say, well, right, just make sure that this is as like, greater than or equal to the original size. And at most, the original size 8 byte line plus the partition threshold. Because if your block is bigger than this, then there's a problem because it should have been partitioned, right? So I think this is a good thing to look for. Current block, perfect, and then we semicolon. Hopefully, Use of undeclared identifier test list. Is it just the C extension being really slow? I think it is. Yeah, it's loading, it's loading. Okay, let's read the chat in the meantime. Um, ooh, wait. What is this? Oh, whoa. Whoa. There's so many conversations. Do you know about Quick? I've heard of it. I don't know about it. Quick is future. Google's UDP? Nope. Quick UDP. Quick's being the future for a while, no? Basically, UDP speed, but TCP reliability. Oh, damn. Also, quite complicated. It's not right now, but it will be in the future for streaming. I just double checked. It was made by Google. Interesting. In fact, YouTube already shifted to Quick. Yo, yes, of course it was created by Google, but I just said its full form is Quick, not Google. I see. Guys, tell me any sort of idea. I got VC networking, 5 developers, but now what? Okay. Read through this. Oh wait, Simbleed. Says it read through this would be helpful to get PCP proc memory page table weak map adds VMAP mapping for every process. Thread memory. Whoa. Those are too many words and they are not very straight. Whoa. Okay. Let me see. Read through this would be helpful to get PCB proc memory page table wick mmap adds vmap mapping for every process. So wait. What do you mean? let me copy this link and take a look at at at, at yeah. So let me take a look at. I'll keep reading the chat, guys. Don't worry. I just want to take a look at this link. Elixir Bootling. Oh, they're making sure I'm not a bot. Okay, thank you. Okay. Oh, whoa. Oh, I think we would have to read this a little after bottom up area allocations. I think, is this just the memory allocator for Linux? If so, I prefer to read it like after we've done our allocator so that I'm not biased on um oh wait, we're doing LRU. Oh, is this a virtual memory pager rather than an allocator? Let me know if yeah. Yeah, I've implemented a virtual memory pager before. So that one I know of. The memory allocator is like the one I didn't know of like that much. Like I knew the concept, but I hadn't really implemented one. But yeah. Wait, let me take a look. So anyone alive? NGMI bad at what does NGMI mean? I don't know what NGMI means. NGMI meaning texting. What does that mean? Not going to make it. Okay. Um why? Are you need to Stephen, what are you saying, please? So, mmap malloc build on top of it, but it's yeah, VM. Okay, yeah. That makes sense. Um, okay. Let's continue. Um, hmm. Oh, you're asking me? No. I'm not Native American. I'm Colombian. I'm from Colombia in South America. But yeah, why is this thing? Is English my first language? No, it's Spanish. English is my second language. Yeah, that's why sometimes I ask like stupid stuff, like, how do you say this and stuff. Um, I wonder why it's not picking up on this. Hello? Wait, yeah, what's happening? Oh, the extension's still working. It's still loading? No, no. This is what happens to us for using Microsoft products, guys. I think we should run code in the analysis and active file. Will it work now? Will it work now? Oh, this is unfortunate. The C extension is not there. Okay, that's fine. That's fine. We'll just continue and hope for this guy to fix itself. No. Okay, rescan workspace maybe. Does anybody time to switch to Vim? Okay. every chance you get. Yeah, no, that's true. That's true. That's true. Then if I run it on the active file, it just stays there. I guess it's fine. I guess it's fine. Anyways. Vim master race. Did what? Yeah, anyways, okay. Let's continue here. So we have the test assert less or equal. We have that upper bound, and I think I'm just gonna delete this line. Like it's annoying me a little. Oh, it just stays there. Anyways, so we perform a check not on the specific size, but we take a look at the bounds of the size of the block, since we cannot really control what the specific size of the block is. Then we assert that it is indeed free or not, depending on what the user tells us. And then we assert that the data is still there. So now what we do is we say, allocate this much, allocate this much, allocate this much. Then we free the block 2, then we allocate block 4, and then by the end, we should be checking that the heap looks like block 1, then block 4, and then block 3, right? Something like that. Block 3. There shouldn't be any sort of partition taking place, and so we should be completely fine, I think. And the extension, since it's just stuck, it just still thinks that there's a 2 written in there. Microsoft. Anyways, let's run the memory allocator and see if it works. Test. Ooh. Well, big problems in the house we have. I expected this much. So there's this little guy. This little less than symbol. That's for some reason in here. Why? Why? Wait, string copy. The string copy copies the null terminator. Yes, right? I hope so, because if not, then yeah, we are cooked. Yeah, there has to be some FI1 error, and that's what I'm trying to see. Yeah, because here what it was actually was the null terminator. And so I'm asking whether or not the copy of a string, because when we allocate, we copy the string into the actual block. So then it's telling us like, oh, in the block there was this, but it needed to be a null terminator. So my suspicion is that string copy doesn't copy the null terminator. I guess just to make sure, since we already know the size of the string, yeah, so actually this guy should be -1 since we allocate that much size, and in the random string, the null terminator counts. So then we need to subtract 1 from it. Well, we create a random string of like of size minus one many characters, and then the off by like the null terminator is gonna be the last one. So I think that may have been the mistake. We make MM test, we run it. Yay! so so that's the way we're gonna test it. I feel this is way better, right? We have like a little toy guy that does exactly what it's supposed to do, and then we just check that the toy guy is like looks exactly the same as us. Um, this is a little tiring. Writing tests is, you know, mm-mm. Mm, okay. So that's what a heap looks like right now. So I'm gonna put it here, right, to test. Then let's keep doing stuff to the heap. So what happens if we free both B3 and B4? Then we should see a single block that is just really big and it's free. So now we're gonna do we're gonna do B3 of B4, and then we're also gonna free block 3, right? And then we are going to expect the heap to be of size, let's see, to have only 2 blocks. And those 2 blocks are going to look something like, you know, B1 here, and then B4. The thing is, we need to account for the fact. Ooh, okay, this is really bad. So remember that whenever we free 2 things that are right next to each other, just like this guy, these 2 guys, whenever we free them, we need to merge the blocks together into one block, right? Our current toy allocator doesn't do that. It simply frees them, and like it just doesn't do anything else. So we need to indicate it to like merge 2 blocks together. Um, I think we can do that. And then slowly but surely we're just re-implementing the allocator, which is what worries me. Be coalesce. So we simply have block B1 and then block B2, right? And then the only thing we do is we say like, oh, B1 dot, ooh, it's not the OG size anymore. Well, I guess it is. So this, and then we add B2 to it, to that OG size, right? And that's it. That's what coalescing means in our toy example. Mm. Yeah, but like, because if that is the case, then we cannot test size. And like the reason for that, it's like now we don't really know how big it's supposed to be, right? Like, right? Because if we don't, like, if we do the merging, because then either we don't test whether or not the blocks merge, or like, right? Like, it is the problem. Like, this is where you can see my inexperience with testing, where I don't know what exactly, like, where the line is drawn to what you need to test. Because I want to make sure that the implementation is right, but at the same time, there are things that are implementation specific and that you want to leave behind in case they change. So, is block coalescing one of those things? Because I would expect a decent allocator to always do block coalescing, right? So is that something we consider general enough to test, or is it something implementation specific? Like, I am not very sure. Um, let's see. Uh, yeah, I don't think you should do that. Block merging is supposed to be transparent. Yeah, it would be better to test that the real version with block merging acts like the toy one without. I feel like you're testing the internals too much rather than the interface. Yeah, it is the problem I have right now. it's like you know, it's a little bit difficult. Um, so yeah, I don't know. I don't know. So maybe you guys can help me on like what it is that we should test. Because if I don't test it that way, like the problem with the coalescing is that like now we cannot measure the size, right? Because in the allocator, the size of this block is going to be very big since it encompasses both previous B4 and previous B3. But according to our toy allocator, it's going to be just two blocks that are free next to each other, which is completely different. Like a completely different scenario. Um, and so, do we test coalescing? Do we not? What do we do, right? Um, so have you tried Postman? Yeah, I've tried Postman for the web. Be free. So like, it's yeah. I'm just in a little spiral of confusion. Like, at what point do we stop? What do we actually test? If we don't test coalesce, we cannot test size, so we can only test the data and whether or not it's free. This toy allocator should only implement the interface as directly as possible with no optimizations. Yeah, so the thing is, like, if we do the coalescing, if we don't do coalescing, then arrangement of the blocks inside is gonna be like completely messed up. And what I mean by that is, like suppose you don't do the coalescing, right? And then I try to do something like implement block B5, which is equal to a B nalloc of S, say, I don't know, probably like 60, right? For this request of 60, B4, like the only two blocks that are free are B4 and B3. B4 cannot be used because B4 has size 52, which is not enough for 60. And B3 cannot be used because it has size 12, which is not enough for 60. And thus the toy allocator will expand the heap and create like a fourth block. Whereas an allocator with coalescing would reuse both, like the space left behind by both. And so now the behavior differs like extremely. And this is the problem like that I have. Yeah. So it's like generally I think people test internal allocator data structures with defensive programming just crashing if corruption is detected. See, it seems like I have no, Steven, sorry, it's just that like we're trying to focus on the memory allocator. I tried to respond to your questions. It's a little difficult when we're going in between like two things. So yeah. People test internal allocator data structures with defensive programming just crashing if corruption is detected. Respect, bro. No AI is the my caster and Jordan. Thank you for joining the chat, and thank you for appreciating that. But yeah, so Valley, currently what we have, right? The internal data structure we have is the red black tree, right? That's like the main thing that we have. And it's in fact our only data structure basically to keep track of the free blocks. And that one we have tested before, right? These are all the tests for the red black tree. Where we like, oh, create a red black tree and compare it to this vector, which, should have the correct size, the correct nodes. And you just specify what the red black tree should look like with a vector representing the pre-order traversal. And then that way, we test the red black tree. So the only data structure that we're using, which is the red black tree, we know it works because we've tested it and it's actually easier to test. No, it's very simple since, like a red black tree, it's like an actual data structure so you can check, oh, this node is after this node and this node is after this one. There is not much choice when it comes to implementing one. And now the heap and the memory allocator is a problem. Like, I'm just trying to test that, like, when you merge blocks, the information is like there, the blocks are the size that they should be, and all of this. Um, so yeah, in theory, you should have access to your data structures, maybe through dirty hacks. I would do maybe some allocations, the allocations with your public API and test your block headers and maybe contents for expected values. Yeah, so something like this, right? The problem is to know what the headers should be. It means that you need to keep track of the size of each block. You need to keep track of when did they merge. You need to keep track of, okay, right, when did they coalesce, when did they separate, when did they partition. And that's sort of what we're trying to emulate here, right? We're trying to do things with a parallel to example where like free just sets the blocks struct to be free. It doesn't do much. And then it just calls the actual example and then it compares the two at the end. But with things like coalesce, right, the two versions can differ despite like being correct. So like, knowing what to test is that it seems to me that like according to this, the only real way to test it is to just write a program using our allocator and hoping it doesn't crash. Like it's like and put in asserts of saying like, oh, just make sure that the data of that block is there. I don't know how big the block is. I don't know anything about it. I just know that the data is there, right? I don't know what the size of the heap should be by the point I reach this. I just know that the allocator is preserving my data, which seems like something you could test and something you actually should test, but it seems too coarse, right? It seems too like general to test, like because you could you could like well wait what's going on? Whoa. I just saw one of Ali's message. What is Stephen sending like weird stuff? Um let me check this here in a different monitor because I don't want to show it. Is this or if you guys can tell me like Stephen, what are you sending? Wait, this is not transferring to the other monitor. Please. Wait, how do I okay, perfect. And then we are here in the code. So let me know what you guys think about it. Because it's like interesting. Ring. Ooh, okay. Stephen, you are getting mad. Bye, Stephen. Yeah. I'm so sorry, guys. Like the first time I get out like a troll or like somebody that's not cooperating. Okay. Okay. Let's go. I banned him already, I think. Yes. Great. The world is now a better place. I don't know. Yeah, sorry about that, guys. Sorry that you had to go through it. I was just a little distracted by this. I wasn't reading the chat, um, like that often, and yeah. Sorry about that. Okay. So back to our conversation. Yeah. So that is the current state of things. Like that. It is. Yeah. I don't know. Maybe value. What do you think, or what do you guys think? Because at this point, it seems like the only behavior we can test is what I just said. Right? Is the data good? Is there no corruption? And all of that. I would not test every internal function in detail, just do some high-level calls and compare the end result with expected. Yeah, but like, what would be the expected result? Right? Like, is like my question, because if the expected result is like how the bytes in memory look, then um, we would have a problem, right? Because then we would need to simulate the program, and like it would be byte dependent. Maybe it's not byte dependent. Maybe it's like how are the blocks arranged in memory? But then we encounter this issue, right? Where you have like coalesce, no coalesce, yes coalesce. Um, so that's why I was saying like, oh, we can just implement a coalesce function so that we can, we can keep track of what the heap is looking like. So this is similar to what you rootInfant are suggesting, where we just keep track of what the heap should look like, and then by the end we say, oh, the heap should look something like this, right? But then Valley raises the point that is like valid, right? Of like, well, not every allocator is going to implement coalesce, but then that means that we cannot really depend on what the final state should look like. At least not to this level of granularity. And so the next level of granularity is just the data, right? Does the data live there? Is it something like that, right? Alloc free freebie should result in one free block of size. Yeah, exactly. That is what we're trying to do here, where we say like, okay, if you call free on these two, then you should expect these two blocks to coalesce, and then like at the end, there should only be two blocks. One called B1, one called B4, and B4 should be big and B1 should be small. Like that is sort of what we're trying to do. But Valley was rightfully saying, well, maybe you shouldn't do that. I think we're going to go ahead and implement this call list function to say like, oh, you should have a big block. I'm going to do it based on the assumption that like we want coalescing in a memory allocator. Maybe there are allocators that don't do it, but like in our memory allocator, we do want coalescing to be like a key property of it, like a decent memory allocator. So a case can be made for either side. I think our life is going to be a little easier if we just have this coalesce, so that we can perform operations on the blocks. Or Valley may have a better point. Let's see what was this reading. I think the best way to test this would be to have a simple struct to represent API calls that can be consumed, either be run normally or on the toy allocator. And the real allocator should support dumping its whole internal state in a form identical to the internal state of the toy allocator for comparison. So there is the problem that like the normal allocator would need to do like for example, with coalescing, right? Whenever the normal allocator does coalescing, then it should say like, oh wait, which blocks did I coalesce? So then when it dumps the things, it like is able to partition them when it transforms it to the toy allocator's output. Which then becomes like, well, if you're keeping track of that, why not make the toy allocator implement the coalescing, right? Or which is the same, right? Have a toy allocator, have the actual allocator, then have something in the middle, which is sort of like the API that you mentioned. And the API keeps track of the operations that were performed, and then it keeps track of what the state of the two should be. Should be like, oh yeah, this guy should have these blocks coalesced, and this guy should have these blocks freed, and then at the end it just translates between them. But then that's sort of what we're doing, right? Where we just keep track of what our implementation of memory allocator should do, which is these blocks should be coalesced, these blocks should that. So we're at the end doing that. So that's the problem. Your red black tree is global variable. It is a static variable inside the memory, the mm.c file. I think I have it here. Where is it? There you go, here. It's a static variable. So you cannot access it outside of things. But our red black tree implementation is already tested. Like we know the red black tree, or like we have developed tests for the red black tree. So that part is like kind of fine. The thing I want to test is like, have we performed the actual things? Have we does free actually merge the blocks and like do that in the correct way, etc. So as a side note, the extension still hasn't loaded. that's so that's so funny. Anyways, mm, yeah, it's still loading here in the bottom. You can see it. Um, so yeah, that's like my issue, right? That's what I think is the problem, right? Um, let's see. I mean, for a set of given API calls, you can determine how the final tree should look like. I would just access the real thing instead of re-implementing it to allocator. Yeah. So the thing is, the red black tree only keeps track of the free blocks, right? It doesn't keep track of like any other allocations. It doesn't keep track of anything else. So maybe we would be able to know the state of the free blocks, but not the just not the state of the allocations and whether or not you know we have everything correctly. um yeah, so I don't care about what the tree looks like because we've already tested the tree. So like we know that the tree behaves the way it's supposed to. So if you insert something in the tree, we know that it like performs all the rotations that are necessary and stuff. What I'm worried about is, are the values inside each block correct? Like if I have two blocks that are free, are they merged in the end and is their size the correct size? Or if I have three blocks, the ones of the extreme are free and then the one in the middle gets freed, does it merge actually, right? If I have Realloc and I have three blocks each of size 40 and then I try to reallocate the middle one to a block of size 50, there is no individual block of size 50, but then I know that the allocator should go to the first block, copy the data, and then get rid of what it has, right? So it's more like those behaviors rather than the red black tree. Because the red black tree we know and we have the tests for it. It performs all the rotations, and it does so with blocks that are in memory. So we know it's there. It's more so, are the blocks behaving the way they should? Are they merging? Are they updating their size? Are they keeping track of whether or not they're free? Is everything like in place? So that's why I'm like doing it this way, right? Where we say like, oh, free block 4. And so we just say like, oh, at this point in time, block 4 should be free. And then we actually free it. And then at the end, we compare the two. Yeah, but that would involve doing the coalesce, which I honestly think it's fine. I think like there's a part of me that says yes, another that says no, for evident reasons, right? It's like difficult to determine how to even test the memory allocate. um, because once again, if we don't want to test like those specific things, like are you keeping track of your size, are you keeping track of whether or not you're free, we would simply have to run this against some sort of real life program and see that it doesn't crash and see that the data's still there and then say, great, good enough for me. But then we wouldn't be able to know if maybe the allocator is being inefficient with the memory. Maybe it's not merging two blocks, something like that. Um, Tests nowadays will be done by AI. Wait. Let me read. Tests nowadays will be done by AI, but I guess it's good to learn how it works. Yeah, I guess so. But there's also a notion in which you say like, to have an AI create tests, right? Like you need to understand what is it that you want to test. Like there's also a sort of value in test design, just like we're seeing here, right? Because if we test too narrowly, then any sort of future implementation is just gonna break. If we test too coarse, then things are not going to be tested the way we wanted to. So I feel there is a lot of value in that process, as you're saying, right? To learn how it actually works and to train sort of our decision making too, or at least mine, right? Because I have no experience with this, so it's good to do this. I would not recommend the comparison with real allocator approach because I assume the main goal of all that is learning, and that approach is not transferable to any real world scenarios. Yeah, you usually don't build something that has bulletproof alternative that you can easily compare to. I think you're worrying too much about the correct way to test it rather than first principle, like tests covering tricky parts and being easy to write. So you're worried if your regulatory operations are actually cold. Yeah, it's too good at creating tests of negative value. I have more tests than I product. So I'm not worried about the red black tree operations being called. So I'll explain what my concern is. So my concern is the following. We know the red black tree works, right? But the red black tree only keeps track of who the memory blocks are, right? What I want to test is rather like, when you're calling free, is the block that you're giving me back, like, did you actually free the block? If you had a block to your right that was free, did you merge with it? Right? Is the state of the heap valid after that? Um, you know, I- so stuff like this. And for example, with Realloc, right? When you realloc, maybe you realloc to a huge block. Did you partition that block and merge it with, right? Is the state of the heap still the what it's supposed to be? Um, are you wasting space? Are you not wasting space? So stuff like that. Um, More of like unit testing each function to see that it actually does what it's supposed to do. Um, so yeah. For example, if I have like say three blocks, right? If I have these three blocks that we've been using, yeah, there you go. If we have three blocks, let me erase this and this. I don't know what it's. Oh, the computer's really slow. Okay, there you go. Suppose we have these three blocks, right? I just want to test like, okay, right? If you have three blocks and say this one's each of them is of size 40, right? And this is allocated, this is allocated, this is allocated, and then this one gets freed, and this one gets freed, right? And then you call realloc on this guy for a size like 60, right? In this scenario, you have more than enough space to go to the first guy, merge with it, copy the data, and have an 80 long block that stores the 60, rather than expanding the heap. So like you shouldn't be expanding the heap in this scenario because you have enough data. So we're testing things like that. Or when you realloc, did you change the free block of sorry, did you make the block free by accident, right? Like all of that stuff. Let's read. Uh, for your use case, testing internal details is actually fine if you define a helper API that exposes some internal space in a convenient way, and then you compile them conditionally with if-def testing or something. Then helper methods. I'm not good at testing to be honest, but what I do for these things is replicate a specific condition. So a realloc where it can grow, a realloc where it can't, and see that in both cases it did the right behavior, knowing what the result should be. Yeah, and yeah, I guess like that's what I was trying to aim for. Like my problem is how, because like when you mention, right, when you mention um wait, let me see. When you mention we do this, right, and then at the end we take a look at what the result should be. My question is like, how do we keep track of what the result should be? Should that include, oh, I have three blocks, each of size 40, and I have three blocks, one of size 40, one of size 40, and one of size 60, right? That seems reasonable enough. But then keeping track of that implies something like this, right? You expect the heap to look like a block of size 1, a block of size 4, right? So it's exactly what we were doing before. And I think this is what Valley is sort of opposing to, that like some of the behavior that we expect is actually something we shouldn't be testing. If maybe it is not adequate to test at such fine level, then it means like, oh, maybe what you expect is not this block is here, this block is here, but something like there is a block at the beginning and it's free. There is a block then that it's allocated, and there is a block that is at least size 20. But then that's sort of also similar to what we were doing, where we were like, oh yeah, right, I don't know your size. I just expect you to be within these bounds, right? But then we realized that coalescing is something that we need to take into account, right? If you coalesce two blocks, their size is going to change. So now you need to emulate that coalescing behavior and say like, well, if you have a free one here and a free one here, I expect you two guys to coalesce. So that's something I was going to do, where I was going to write the coalesce function to be like, oh, expect these two to be coalesced. But Valley rightfully suggested like, well, right, is that something that we should test? Like should we test the coalescing? What like and so now I'm like confused, right? Because what I would do is just do coalesce, write a coalesce function, and then just say like, oh yeah, expect this guy to be free, expect this guy to be free, coalesce these two, and then at the end be like, oh yeah, and the state of the heap should look like this, right? So I think that's like my the thing. So Realloc where it can grow. Yeah, exactly. First time chatter is Alpha RMQ. Welcome to the chat. Welcome to the stream. For this kind of stuff, it might be better to just look at it in a debugger to get confidence rather than make unit tests, because this stuff can change based on strategies a lot without affecting Yeah, so Valley, that we have done before. So we have created like little tests or like scenarios, and we've taken a look at the debugger to see that it does the correct thing. And then I was like, wait, well, right, if you were developing this as a serious, like a very serious project, there would have to be a way in which you can just run tests and see that your implementation is correct, rather than whenever something changes, go and take a look at the memory inspector again, and then take a look at every byte and make sure that everything is okay. Yeah. So I prefer replicating the exact conditions. Okay, different. Wait, let me see. I think I may not be understanding then what you're saying, because I think you may be saying something else from what I understand. Um, Turbofish PK, may I ask something off topic? Of course. How did you acquire so much knowledge in C at the uni? Uh, well, so much knowledge in C is a little bit of an overstatement. I am, if anything, the opposite of that. Like, I just know like the syntax of C, but I think many of the people that are in the chat can be witnesses to the fact that I am basically a C baby. but, but yeah, mostly comes from C++. I got a question. How does one reach to a stage where you can think about making a memory allocator? I want to get good at C. Could you just guide me through what was your approach learning C, any specific material or so? I think there's people in the chat that are even more like that have a lot of experience. I am still like a college student, so I'm still learning. What I can tell you is I just remember, at least when it comes to C, I took a class on operating systems. I really liked it. And then despite not knowing where to go, I just said, let's write a memory allocator. Not sure how, not sure how we're going to do it, but we're going to do it. So it's almost like a throw yourself into the void because you know you have to get out eventually kind of approach. and I've done most of the things like that. So yeah. I'll expand on that maybe a little later. Is it that we've been a little stuck on this, and so I want to solve this and like end the discussion of the testing, and maybe I'm creating like too much drama about the testing, which I think is the case. I'm just being like really annoying. So I want to end that discussion, and then we can expand on that like a little more. And yeah, the Ferrari. Okay, this is the message I was looking for. What I'm saying is automate those scenarios essentially. My point is that this isn't really testing correctness. Okay, I didn't know how to explain, but the last thing I said, do what you did in the debugger, just checking the specific memory and code. instead of debugger. Yeah, exactly. So different array. This is what I wanted to do, right? But then Valley raises the valid point that like, what happens if you change something in the future? So something like previously in our struct, right? For example, we used to store the color in the parent. And so now if we automate the process of looking at memory, changing the color to here, it like changes all of the bytes. And then the tests are gonna be like completely wrong, even though the behavior is exactly the same, because the bk color function still obtains the thing it should. If you mean it like, oh, just check it in this sense of like, you should see a block of this size, you should see a block of this size, you should see a block of this size. That's what I was trying to do. But then I just want to do it the correct way. And like, according to what Valley is saying, this doesn't seem to be the correct way. So I'm trying to understand like, what do I do? Because if this is not the correct way, where I just say, I want the heap to look like this. It looks like this block with this size, it is free, and it has this much memory. And it looks like this block with this size, and it is free, and that's it. So that's what I would do in a normal scenario. Kind of what you're saying of like, replicate the situation exactly, right? There is a block of size 33, a block of size 53, a block of size 12, block 2 gets freed, and then da 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 da, and then expect it to be this and exactly this at the end. So that is what I'm trying to what I was trying to do. By the way, how does your allocator get memory from the OS? BRK or mmap? Currently we're just doing BRK. It should be mmap, but we're gonna change that. If you make those kinds of changes, you have to change the test. To be clear, I'm probably talking overconfidently. Don't worry, Valley. Like, yeah, I'm just trying to like understand what it is that we have to do. I think I think it is a discussion in which both sides have like good arguments. It is something that we cannot really determine like so easily, right? Um, our implementation, like we know what we want out of it. We know that like, our implementation will have coalescing. So I feel implementing coalesce is what we're going to do. By saying this, like I'm not saying that it's the correct way, but like we need to end the discussion somewhere, right? And we it's in like 30 minutes and without knowing what to do. And perhaps that's the thing, right? Maybe there is no right way. So let's just choose one. I'm going to go for be a little more specific and like create the exact scenario that you want and then like, expect the memory to look something like that. Because I think it is simpler and it actually, it like measures, it's a little bit more palpable, like, right? Like I can be more confident. Yes, my allocator is coalescing. Yes, my allocator is freeing. Yes, my allocator is merging these two together. Rather than just like, I know the data is there. I just don't know if they coalesced. I don't know if they are still free, etc. So yeah, let's go with this approach. Of like being a little bit more granular. I think like De Ferrari says, if things change in the future, we would have to change some of the tests, but we set it at a middle ground, right? A middle ground where we don't check every byte in memory, because that would be a little too extreme. We check a general idea that it's like, oh, the data is there. Well, that also not, because we also want to test that the blocks are actually doing what they're supposed to do. So then we grab the middle ground. It's just like we try to be granular enough where we assert that the blocks are coalescing, that they're doing what they're supposed to do. But we do so in a general sense. We just, we don't look at the bytes themselves. We just say, okay, your size should be between these ranges, right? I don't know exactly what you're going to give me, but it should be between those ranges. You should be coalesced with your other guy, and so on and so on and so on. So I think that is the way. That's the way we're going to do it, just so that it doesn't become like an eternal discussion. Let me read the chat now.
I define how the allocator works. Rules like if one block is growing and the next can cover the growth, just expand it with the same pointer, if not, different pointer. It should completely ignore things like whether the alloc uses a tree. If you want to test the tree, that's a different set of tests. Yes, completely agree, completely agree. By the way, there might be some standard tests for allocators, or at least see what other allocators use for testing. That is a good idea. I think they usually use like they just run programs with the allocator and they end up seeing that. But yeah, test only things which you don't expect to change in the future. Yes, that is true. So one of those things I think is the coalescing, right? I feel sort of what Di Ferrari is saying, where like I define my memory allocator to be an allocator that expects to coalesce blocks that are free. And so I'm gonna test that the blocks are actually coalescing. Could there be an allocator that doesn't coalesce? Yes, but like I know that for the behavior of mine, this is a feature. Like this is something I want in it. And so we're gonna do it that way. Yes. Random hacker, your approach to testing seems reasonable for the use case. You can't properly test lower level code without being somewhat tied to the implementation. Yeah, that's the problem. Memory allocator is not a simple library where you're only interested in side effects and don't care about what happens internally. Yeah, and I think that's the whole thing that has generated like this huge testing crisis of like what do we actually do? So I think yeah, let's go with that. Let's go with like with it. So whenever we coalesce, we're gonna say like b1, right, and then block b2. And then we're gonna do b1 dot og size plus equal b2 dot og size. Probably. I think so. I think that's the rate plus the size of the header. Great. And so what we're going to do is we're gonna say, oh, expect these two to be coalesced. Right? So first before merged with b3. And then we should expect the heap to look something like this. Yeah. So, you know, allocate 3 blocks, each of these sizes, free the one in the middle, put something else, expect the heap to make B4 have replaced B2, right? So it's gonna look something like this. Ouch, 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 ouch. Yeah. So expect the heap at the beginning to look something like this, right? B1, B2, B3. Then after we perform this operation, we expect the heap to look like B1, B4, B3, each with their respective operations, no? Because like expect heap just takes a look that like the size is actually the same as we originally specified, that the data is still there, that it's actually free, and so on. So yeah, B1, B4, B3. Then free B4, free B3, and call and internally keep track of the fact that these should be coalesced, so that when we perform this expect heap, we're like, oh, it should be B1 and B4. And like this function modified the size of B4 to accommodate for what it should be, right? And so now we expect the heap to look like B1 then B4 with their updated information. And now what we expect is something like block B5 to be equal to bnalloc, and then maybe we allocate for, let's see. So B1, B4 should have a size of B2 plus B3, so something like 65. So then we allocate something like 60. That should fit inside B4. And so when we allocate that, we should expect a heap. Oh, well, we would have to free B4 first. Free B4. Then we expect the heap to look something like this. To look like 2 blocks, right? One of them which is B1, the other one of which is B5, with their respective information. So after B3 is 4, maybe we expect the heap to be of size, block 1, and then only have a single block, which would be B1. And that's it. So yeah, we allocate 3 of them. The heap should look like this. We free B2 and then allocate B4. B2 was 53, B4 is 52, should look something like this. We free B4 and B3, and we keep track of the fact that they should be coalesce, right? And then we expect the heap to look like this, to be B1, and then since B4 and B3 coalesced with each other, now B4 should be the only one, and this guy updated the size of B4. Then we free B4, so now that we have B4, we expect the heap to look something like this, where it should be, because we also need to keep track of which blocks are free. So I think before. Now let me just erase this. So we free B4, then we allocate B5, and then we should expect the heap to look like this, because we freed B4, and then now B5, which is 60, and B4 was of size like 65, it should fit in there. So that's what we expect, right? It is bound to coalescing being a thing, but like, you know, we just say like, okay. And I think just to, yeah, what Random Hacker says is very good. Like, we have to be somehow tied to the actual implementation. Alpha RMQ, just be my mentor already. Thank you. I mean, yeah, I'm not sure if I would be ready for something like that. That'd be kind of crazy, but yeah. You know, gotta have a lot more experience myself, but we're building the way there. Let's try and run this test. Let's see what happens if we run it. I'm pretty sure it's gonna fail. Like, we did something weird. One failed. Expected 108 to be less than or equal to 76. Okay, so we start encountering. I don't think this is a problem with malloc. This is a problem with our test. Line 74. So here, we're testing less than. The extension is still loading. This is absolutely insane. Okay. Wait, I'm gonna reload the window because it's kind of annoying. Give me a second, guys. I'll be back in 1 minute. Okay, give me 1 second for a break. Whee! Hello, hello. Okay. Oh, these things are about to die. Oh no. I'll put the other one in. Then I can put them back. Okay. Perfect. Perfect. Zoom, boom, 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 boom. Zoom, boom, 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 boom. Perfect. Okay. If the allocator could dump its data as text, you could implement these tests automatically as snapshot tests. Okay. So you mean create a function. Yeah, create a function to allow the allocator to simply print like, there is this block with this size and it is free. There is this block and so on. Print the state and then just make the test be whatever that output is, right? What we expect the output to be. But then it seems like you're arguing for the other side now. Because then it would be like extremely implementation specific. Because it's like this specific implementation, this is what the memory looks like. Um, so yeah. It also seems like the only thing we needed to do was reload the window. That's unfortunate. Uh, but yeah. So where are we failing? Can we run test? I think so. I just want to take a look at the call stack after we failed. Mm. Mm. Okay, let's let it run. Oh, what? Oh, it doesn't. Okay, okay, it doesn't trigger an assert failure. It just tells us what happened. That's unfortunate. Mm. Okay. Yes, it's fine for snapshot tests to be super specific because it's not necessarily a bug if they fail. I see. I see. So they could be just implemented alongside these guys that we're doing. Think of it as a warning, like, hey, this internal thing was affected by your change. Is that supposed to happen? I see, I see, I see, I see. Interesting. So we can do snapshot tests after we do these. Like we just put the two together. Um, Generally, there's a command to reset the snapshots so the new versions also look correct. I see what you're saying now. Okay, that makes sense. So if we're really set on a given behavior, then if a snapshot test changes, you're gonna be like, what did I change? And then you go check it. Okay, I see. I see. Nivim uses a whole lot of snapshot tests. Interesting. I imagine like for the UI and stuff, maybe. Because I imagine it's useful for UI, right? Because then it's like if you change something, then it's gonna be like, oh, this thing is like 10 pixels to the left. Why? Anyway, but yeah. I digress, I digress. Um I want to first discover what it is that's causing the issue. Because this is no longer fun. This is no, this is- come on. If we run test malloc, maybe here. Okay, it gives you a nice global view of where your changes are reaching without fossilizing things. Yeah, that makes sense. Seems like a good pitch for it. But yeah, let's see. Do we? Ooh. Okay, so are we just failing the first assertion? What is going on? Wait, are we genuinely just failing the first assertion? That'd be really sad. Okay, let me run this again. Okay, we continue and then we get here. And then we it seems like it's fine. Then we now look that. And we're not failing this one. Perfect. Right, nothing has been printed or something like that. Yeah. Then when we coalesce these two, we're free and coalesce. And so the size of B4 here. B4. Oh, I cannot take a look at it. What? What's going on? What's going on? Okay, be free. So that one doesn't fail. And so the one that fails is the last. I expect heap. Yeah, that's the guy that fails. Right? Hello? Oh, dude, this is so confusing. How am I supposed to know which one it is? Because if we run it, it says it fails, but like I don't see where it fails. Ah, ah. Let's see. The three of them are together, sure. Right. Then we free B2. B4 takes its place. Then we free B4. Then we free B3. Then we go on this. Then we put B1, B4. I think I'm being too strict with the upper bounds. Like 16 months, yeah. I think it's fine enough. Okay, it still fails. Expected 108 to be less than or equal to 92. Oh my god, what is going on? You expect macros could print the location. Yeah, like that's this guy, like, because it is telling me the location is line 74, but like this is inside a function. This is inside an expect heap function. And so maybe I should convert this into a macro. And then but then I don't know how to print the line. Right. I wouldn't know how to print the line. Which is unfortunate. Like I thought Unity would let you, because you know how in the debugger if you fail an assert, it just like crashes the entire program. Here it like just tells you, oh, there was a failure, and then it continues running. Maybe they could print the call stack. Yeah, but yeah, I don't want to sound too ignorant. I just don't know how to print the call stack. It's like these guys, maybe you guys that have experience with Unity, because some people suggested it. Wait, you could put an int3 in the inserts. In the inserts? What do you mean? Wait, what do you mean in the inserts? The expects. Okay. So you mean like putting an identifier and then printing it? I'm not. What do you mean? What? Yeah. So I mean, another one could be like just putting an ID and then like being able to that get annoying really fast. But int3 puts you into the debugger. It's a breakpoint. Oh, really? Like this? What? Huh? Wait. Um. Insert or insert. Use a debug break. The compiler will insert an int3 instruction. Okay, yes, but like when you say use a debug break, like I should just, you mean like put in the source code debug break, something like this. Yeah, I'm so sorry, I'm not understanding what you guys are saying. Because I mean, another thing I could do is just like put a print statement here and be like succeeded, but like empathy finished test malloc, and then include the breakpoint right here. And then I just make make test, then run the debugger on test. Give it a second. And then be able to just run right here. We see that expect doesn't make it fail and it doesn't print anything. And then this one doesn't fail. Everything's fine. This one also doesn't fail. This one doesn't fail. And this one doesn't fail. Never mind. Yeah, Unity is not printing anything. It's like, I'd argue like a little bad. Yeah. Let me see what you guys are saying. Sorry, I forgot it's ASM in 3. Okay. I see. ASM int 3. So if I do something like this, you mean? ASM and then int 3. I mean, the autocomplete recognized it. Maybe I just need to include a semicolon. Yeah, I'm on a Mac. Yeah. No, my Mac is like M2. Yeah, so Unity just behaves very weirdly because it like just, okay, I'm just gonna do something for the sake of the sanity and the fact that like I don't want you guys to just keep to to be looking at me just here completely like dumbfounded. And how about we just do this, right? Assert that this guy is greater or equal to this, and so this, and then we just say assert that this thing is indeed the case. So this size is smaller than this other guy, right? Test that they are equal, and so we just do assert, and then these two guys are the same. And then here we just do assert that the string comparison between the two is equal to 0. Yeah, I feel, and then when we make this, now we can actually run the debugger and it's gonna crash wherever it needs to crash. So here it doesn't crash, here it doesn't crash, here it doesn't, here it doesn't, and here it doesn't. Wait, so it behaves correctly, right? Because like if I run test, mem SBreak failed, ran out of memory, segmentation fault. Ooh. Yeah, I'm so confused. I'm so confused. In 1 second. Yeah, it's because we didn't call setup. Okay. Setup. Version failed, right? Function expect heap file this, and now we can run the debugger. Hopefully, once and for all, to end all of our misery and suffering. Oh, I see what's happening. So when we make test in the make file, we forgot that like we actually have. We should actually put this in the bins folder, not that guy. Bins / that. That's kind of frustrating. And then we do ./bins / test. Okay. Perfect. And now if we run the debugger, hopefully it runs the actual file that I wanted to run. Yeah, and then if we continue. Yeah, okay, now it works. Yeah, there you go. Okay, now we can take a look at the call stack. Finally, okay, this one fails. Fails the first one. Dangerous, dangerous. I think that we can go back to Unity now that I realized that the problem was not Unity, but the fact that we were executing the wrong file. Slow descent into madness. Happening slowly but surely. We just make the MM test, then we run the binary, and it should have an assertion. Yeah, okay. And if we run it in the debugger, hopefully it's able to tell us what went wrong. Unity begin, continue here, and then we run it. Yay. Okay, expect heap to be this. And then does it already print? No, it doesn't print anything. Continue, we continue, we continue. Never mind. Never mind. Yeah, Unity is not cooperating, so I'm just gonna use normal asserts. Yeah, I just don't want to complicate it. I just want to use normal asserts so that we run it with the debugger, and then when it crashes, it tells us exactly where, and then we just use the stack traces to determine where that happened and how that was. Um, I just don't want to make it more complicated than it needs to be. At least not today. So we test malloc, right? And then here, notice that like if we go here and here, it like boom immediately. Right? There was a problem with the size. And the call stack is this, right? It happened here and then it happened here. So we're failing here for some reason. Why? My own. I forgot that debugger can catch crashes, anyways. Yeah, yeah. So that's why I was like, okay. I mean, Unity is not catching the crash; it's just letting it slide and then reporting it. But I don't need. I want it to crash immediately so that we know where it was. I created my own. Sorry, my own assert so that it just breaks in the debugger instead of crashing. If running outside of a debugger, a break instruction will crash anyway. I see, I see, I see. But yeah, currently I don't think I have enough energy to create my own asserts to do that. I can honestly conform with this one, to be honest. So this assert is the one that fails. For what? Why? For what purpose? For what purpose? Anyways, we get into malloc. We expect that heap. We see that it crashes. What are the actual values at play? So I is number 2. So it is complaining about the last block. It's complaining about B3. It's saying that B3 is not actually there. Oh, I think I know why it is. Actually, no, I don't know. Okay. Size 16. So when we assert this, we have I is 2, N is 3, that's correct. Block I. So let's take a look at what blocks I is. Blocks. Oh. I think we can just watch it. Blocks.I. What is it? It's OG size is 12, right? And then we tested the OG size. No, it's the other way around. We test that the size of the block is at least this much. There you go. See, it's way easier with a debugger. I'm so sorry, guys. Like Unity, I'll investigate more on like how to make it work and all of that. But like, I just want to know when the asserts fail and take me there. Yeah. So let's continue. Let's continue. Let's see what happens. So here we continue. Then we do this. Then we expect the heap to be a certain way. Should be fine. Yes. Continue, continue. Expect the heap to be like this. Should be fine. Expect the heap to be like this. We fail. What? Okay. What happened now? Now it's saying that we have that it's too big. Okay. So it says that it is allowed to be at most this much. Okay. So what is the size of the current block? Like the actual size? Ooh, it's very big. It's like 108. Whoa. While the size was 52. And this is where? This is here between B1 and B4. Oh yeah, and I is 1, I imagine. I see. So when I is 1, yeah. Okay, so it's believable that this one can be of size 108, kind of. But that feels a little bit exaggerated, right? This shouldn't be happening. B4, it's like size 52, right? We free B4 and B3, but like B3 is of size like 12. Suppose that because of alignment and stuff, it's like 20, right? And maybe 52 is not 52, it's actually like 70. But 70 plus 20, it's still 90, which is like not that much, right? Like at least it doesn't get to 108, and I was very generous with the amount of memory that I had. So this one could be a mistake. Is there something we're missing? Why is it so big? I think this is the point in time where we go to the memory inspector and take a look at our own implementation too. Let's run it. Yum, 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 yum. We run this. And we know what the address of the heap is this thing. So I'm gonna add 0x 1, 2, 3, 4, 5, 6, 7, 1, 0, 0, 5, 6, DCE 0. Perfect, this is what the heap looks like. And so now, when we allocate the 3 of them, we have 1C for this first block, which is 24 if I'm not mistaken, right? 16 plus, oh no, it's a little more, 28. 28 actually, it's 28. So it's 28 bytes, and we see that it ends, where does it end? Where is the footer of this thing? Hello? Where is the footer? 1C, right? It's 28. So it should be something like here, but this is 3C. Oh, yeah. And then the next one is 53, which is 3C, which is 3 times 16 is 48. And then 48 plus 12 is 60. So then it rounded it up to 60. So remember, 28 plus 60, that's 88. And then it ends, I think, here, right? And then this is the next block, which is of size 14 in hex, which is 20. So that is B3. So 88 plus 20, that's 108, right? And that's it. That's the end of everything. At least it should be. Right? Because there wasn't anything else. We just allocated the blocks. Everything should be completely fine. Oh, but there is a fourth block. It seems. What? Because 14 starts here, and then we write all of the data. Right? We write. And then it ends here, right? Exactly 20 bytes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. 20 bytes. But then I see the header of another block. It says 15. Why is this a block of size 15? What? Um, is this just a coincidence? I hope it is. What is the size of the heap currently? So non heap size. 168. How? Brother, we allocated blocks. What? is there is there something wrong with this? Like, what is happening? Huh? Something's wrong. Something's wrong. Nothing is right. Hmm. Or maybe it's executing this instruction before it even happens. Like, what is going on? Yeah, I'm gonna comment out all of this because like previously it happened to us that we had like a variable declared and then for some reason that changed the behavior of the program. It was like absolute hell. Um, if we make the test, then we run this. Mhm. So we have the 3 blocks and the heap size is 120, which is reasonable. But then we add that it is 168. Ah! Why? 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 Ah! We had a block of size 28. Then we had a block of size 60. So another heap of size. Then it was 88, right? And then for 88, yeah, okay. I'm just gonna go through each block allocation, take care of what the heap size is because it's what is going on? We set up with Realloc. Okay, heap size is 0. Then we expand it to be 56. Good. Actually, bad. Why is it 56? Why is it 56? No, good. Okay, yeah. So the size should be 28 when we align it, plus the 4 bytes of the header, 32, plus the 20 bytes that the ghost node occupies, that's like 52. And so, 56, sure, reasonable. But then what, 32, right? Then after this, the size was 56. We needed to expand it by 60, and so we end up expanded by like basically, 120. Okay, so 120 is a reasonable size. And then we add whatever this guy needs, which is, a line that's going to be 20. And so the 120 plus the 20 that we need is going to be like 140 something. Yeah. We're doing a byte alignment. So it's like the first block ends up being like 32, right? Because we also need to count the for CMD reason. Yeah. It's just like we are currently just doing a byte alignment because like usually custom alloc return a byte alignment. And like it was just something that we decided at the beginning. We have a parameter that does alignment, so we can just change this to 16 and then we'll be fine. But yeah, that's like the whole reason. Well, like that is gonna be in the future, but like now I just want to get this working. To be honest, yeah, but yeah. So after this expansion, it will be like one. So what is 30% of 120? It's like 40 something, right? 40. And so now we expand by the expansion factor, which is 160, and then half of this. Yeah, which should be like 166 and 168. Okay, perfect. And so now we can expect the heap. Sir Elfman, welcome, welcome to the stream. We're currently in like a pit of hell. Um, yeah, it's really bad. It's really bad right now, Sir Elfman. um, okay, yeah. Guys, we have another issue. We have another issue. I'm gonna, I'm gonna start crying. Basically, what's going on is remember that we decided to implement this one optimization, right? Um, there's one optimization where we said if we ever need to expand the heap, and I think it's over here. There you go. If we ever need to expand the heap, we have multiple options. So we think of the heap as a vector. You know how when you overflow a vector, when you're like, oh, I need more elements, the vector first tries to double its size, and then if your request is bigger than that, then it like accommodates to exactly what you need. So that heuristic of doubling the size is something we want to do with the heap too, right? Because if somebody has allocated, enough to reach the limit of the heap, then we want to apply that heuristic so that we don't have to do as many syscalls to increase the breakpoint, right? And so for that reason, we created this thing called expansion factor that like, if you ever need to expand the heap, first we consider just, multiplying the heap size by this much and adding it at the end. We just made it 0.35 for absolutely no reason. Just some arbitrary number. We can just change it whenever we want. So we expand by that much. Or we can accommodate exactly to the size that you need. Or it must be the minimal amount you need to expand it by. So the problem with this, with the expansion factor heuristic, is that when the heap expands, right? So in 120, if you get like 35% of 120, it lands you across the 166 range. So it means that when it expands the heap, it's doing it through the expansion size. And so now the size of B3 is not like this much. It's like, yeah, so that should be the max, not the min. What do you mean? Here? Or where? Never mind, it is. Yeah. And so, right. Yeah. Okay, so that explains why. Okay. Focus, locking. Let's go to the memory inspector. Take a look at this. 1, 2, 3, 4, 5, 6, 7, 1005, F1A70. Perfect. This is the heap, completely empty. Continue. First block. It's right there. 1C. It has length 1C. Okay? Next block. It has length 3C. Okay? This is recorded in your minds. You're like, oh yeah, length 3C. Yeah. That makes sense. Okay? And then this guy. So remember, we expanded the heap by the expansion factor, which means that what we actually needed to allocate was a little smaller than the actual space that we gave it. So we're going to have 14, which is the closest to 12 that we can do, 14 being 20. So we give a block of size 20, and that explains why there is a fourth block. There's a fourth block because that is the guy that remains after you expanded by more than what you needed. And so you partition the block and you give to B3 that little portion, and then just there is an extra block over here. So now what it is saying, it's saying like, oh, you're telling me there's block 1, block 2, block 3, and that there should be no more blocks, but there's actually one more block, which is the side, the block from that expansion thing. And the problem is that the expansion factor can change, which means that like the size of that thing is gonna be different every time. And so now the final block, if it is freed, it's gonna be some amount something. Okay. Okay. Yeah. No. Guys, I'm gonna be completely honest. I think we would have been better off by proving the correctness of the program through something like Rock or Daphne than using tests. Like, we could have just done formal verification at this point in time. Like, could have just pulled up Rock and Daphne and like proved that the memory allocator is like correct. Um, but yeah, because B1, B2, B3, and then there's an extra free block, which is of size like around 20, and it's free, so true. And then he also has we don't care about the data it has because it's free, right? So that assertion should pass. But like now we're specifying. Oh my god. Okay. Let me try something out. Let me try something out. I. anyways, have you done formal method stuff before? It's a rabbit hole I kind of want to fall down to. Yeah, let's have a conversation. Let's have a conversation. I'm so tired of this. I do not want to look at this, bro. This is, bro. This is what like Linus Torvalds nightmares probably look like. Like probably, it's like, oh no, some random testing. Okay. Ah. Anyways, yeah. So that test isn't so bad. No. Like what I'm saying is like now we need to account for the free space that remains. But like the free space that remains is dependent on the expansion factor. So if we ever change the expansion factor, which we probably will, that space will be bigger. And now all of the tests are gonna fail because they're expecting the last block to be of a given free size. But now if the expansion changes, then it's gonna be like bigger. And so the test is like, oh no, it's actually right. We're not testing it's gonna like we don't test its contents. Yeah, I guess like we just make it be so that we just don't specify what the last block is. And so here, let's see. Um, yeah, okay. And so, wait, but we are not testing its contents, right? Wait, what's going on? We are not testing its. Whoa, whoa. What did I do? Guys, did I make a weird change? Why are these warnings appearing just now? Bro, please tell me I didn't break anything. Bro, please, God, please, no. I mean, this is completely fine, but like, wait, what did I change that made the warnings start popping up? Did what? What? I'm zaked, yes. And then nothing else. Yeah, dude, what have I done? No. Yeah. No, I understand what you meant by the contents, yeah. Like so I think we can just do that. We can just say like over here in the test, when we expect a heap, we can be like, oh, the final block, if it's a free block, just verify that it has nothing after. And then if it's not free, then just verify that it's the last one. And yeah, okay. And then if we run this through the debugger, so what should happen is the following. You'll be amazed. So we test mal. Okay, now we allocate them all, whatever. Then we enter the expect heap function. Okay. So the current block is going to be the first block ever, and now I is 0. Should be 0, yeah. So we test the first block, which is block B1, B2, and then B3. So B1 has the size it should. Everything's fine with B1. B2, it has the size it should. Everything's fine with B2. Now B3. B3 is I2, yeah. So B3 has the upper size that it needs because the current block is 20 and the original size was 12, so we're fine. 20 is definitely smaller than the OG size, which was, I think it was also 20, right? Blocks in I, OG size is 12, right? 12 plus the partition threshold, which is something like 20, yeah, plus 16. So BK size is definitely under that. Fine. Then the string comparison between the two should be fine also. And then we need to leave the function now. Right? Because like I is 2, so when we increase it, it's going to be 3, and then we leave. Brother, why was this? What? It was failing. It was failing. A few moments ago, it was failing. What? Oh, brother. It was failing. Wait, you guys saw it. Like, now it doesn't fail anymore. Okay. Yeah, whatever. So, although we do have some interest in testing this, we just want to assert that either current block is just a no heap pointer, or sorry, no. Yeah, either current block is a no heap pointer, which means we have reached the end, or the current block is free. And it has no next block. So in the next block of that thing, it's just nothing. Okay. And then let's run it. And then test. Oh. Bins/and test. Finish test malloc. Okay. It's working. Guys, it's working. It's doing what it's supposed to be. It's behaving. It's behaving. So anyways. Okay. We need to well, not we, I need to calm down a little. Calm down a little. And reconsider my life decisions because this is not a great scenario to me. Let's see if any of the other expects fail, because we had commented them out while we were. Okay, make MM test. Great. If I run MM test, surely it will work. Oh. If I run MM test, surely it will work. Okay. No, it's fine. It's totally fine. It's totally fine. I know exactly what the issue is. Okay, the issue is like, do you remember that free block that ends up being here, right? That ends up being here at the end, right? Of the B1, B2, B3, whatever, here. Right? There's like some guy here that we just don't check. Well, guess what? He's come back to ruin our day. Because when we free B2 and we replace it with B4, things are fine. Things are totally fine. But when we free B4 and then we free B3, we coalesce these two. Isn't there something strange? Aren't you noticing something strange? Yeah, exactly. B3 still has as neighbor the little guy that's living here. So when we free B3, we coalesce B3 with the mysterious guy whose size we don't even know, and then we coalesce it with B4. So now we don't even know what the size of B4 is because we attach to it something whose size we don't know. And so now we cannot measure the size of either. Like, okay. And then here is where we fail. Like, I assume that's where we fail. I'm so confident. I'm just gonna run it, and like we'll see that that's exactly where it fails. If it fails early, it's gonna be even worse. Let's take a look at the call stack. Yeah, exactly. Like it just fails here because the size of the four is something completely different. Yeah, guys. Okay, like I think we're going to. Bro, like I don't even know what to say, bro. um, I think I think we're just gonna give up. You know, abandon software engineering, completely use this career. This is what we're gonna be doing all day. Anyways. Okay, we need to focus. We need to focus. We need to focus. I'm kidding, by the way. Don't abandon software engineering. Memory corruption goes brrr. Yeah, unfortunately. So I think it's just our testing approach in general. Like, it's just not feasible this way. Like, we just cannot test it this way. Like, either we do snapshot testing, which we could set up, but like I'm genuinely tired of testing, so maybe we can do that tomorrow. Give it a snapshot test. And instead we focus on like more a little bit general tests where we simply plug in our memory allocator into some sort of toy program and see that the program works correctly. I think that's the only reasonable thing to do now. Um because it's getting like genuinely annoying. I think it's for you guys as well as me. So let's just keep the testing for tomorrow. Okay, we'll make that mutual agreement. Um, let's eat frosted flakes in the meantime. Relax and understand that life is, if anything, a chain of decisions that have taken us to the current moment, and that we should cherish it rather than feel, you know, depressed because testing is an actual thing in the world that Satan himself brought into the surface. But yeah. Anyways, I'll stop being too dramatic and let's just focus on what we need to focus on. I'll abandon the testing for now. Let's just do something else. Okay. Mm, yeah. So I think I think we should take a break because I'm currently like absolutely like destroyed inside after failing so miserably at testing the memory allocator. Um, we're going to think about the testing more deeply. We're going to do it tomorrow. For now, let's take a break. Let's take a break. So I want to think, is there anything other than testing that we need to do? Um, and the answer is probably, right? We need to fix the alignment. And that's kind of it. We need to fix the alignment. That's all. Yeah. So yeah. Um uh okay, let's take a break. Let's take a break. Let's take a break. And yeah, probably, stand up, look at the landscape. I'll play some game and then we'll come back. Okay? Um let's take a 1 hour break. So we'll be back at 2:20 2:20 p.m. Okay, so I'm gonna put it like I think I can set it up here in my script or something like that. I'll just start the countdown and make it be like, say, 60 minutes. Okay? 60 minutes. 60 minutes. Okay. Let's take a break now. Pause, relax, go grab a coffee, go do something, and we'll be back in an hour. See you guys.